This conference will now be recorded.
Yes, and I'll get you a copy of that, Blake, for sure.
Okay, thank you, sir.
The only reason is I have all the, your faces and stuff all shrunk down. So I couldn't find you to make you that presenter. But anyway, we'll make this work. So,
Okay.
all right,
Hey,
let's again, feel free to interrupt me at any time. I'm kind of just using a single screen, so I don't see any hands being raised or anything like that. So just feel free to turn on your mic and interrupt me at any time. So I'll move right along and
Are you planning for some breaks, Rick, and things like
yes,
that? And okay.
yes,
And then
absolutely.
you'll turn your camera on and kind of,
Yeah, we'll do little 5-minute
wake
breaks.
people up.
Yeah, after each session, and the sessions will be about an hour. So, we've we've said this for a long time that the mind can only absorb what the buttocks can handle. So if you guys are sitting and listening to this for a while, we say that at classes as well. So we understand. So let's go through, just go through the bullets and make sure, just get an overview of what we're going to cover in this first session. Okay. First thing is this thing we like to refer to as universal hydronic formula, and everything starts there. So this is always a good place to start. If you really can't do anything as far as delivering energy until you work out what we use in North America as US gallons per minute. And so we need to figure out how we take heat loss and turn that into it. So we'll get into all that. There's certain things within the liquid that affects these numbers, and we'll show you how that transpires. You folks use glycol, I'm sure of it, and so you want to see how the glycol affects the number that you're using. Okay, and when we're actually moving fluid through pipes, we call that the speed of that, we call that a velocity, and that impacts the pipe sizes. So depending on, what we want to stay above or below, you'll see how that all comes together as well. And just a real short bit on the difference between a pressure drop estimate and an actual calculation. We'll show you the differences there. Okay. And then finally, if we have enough time for this session, we'll get into CV and how that affects pressure drop as well. So let's jump into it. So design process, right? These are the building blocks it takes. And remember what I said about everything starts with the load. Well, the load in this case is we got to figure out how much energy we need to deliver. And I will say there's somebody that has their microphone on and I can hear some background noise. So just like I said, turn your mics off, and then when you want to interrupt me, feel free to do it. Sounds like you got it. Appreciate that. So then once we figure out what the loads are and we do those calculations, then we can start selecting the type of heat emitter, and a lot of times the type of heat emitter will drive the style of boiler. For instance, if I'm doing a radiant floor application, I'm doing a lot of low temperature things, then my boilers make sense to be a condensing piece of equipment. And nowadays I've got to throw this out there, maybe a ground source or an air to water heat pump, because those all require lower supply water temperatures. So those are things to think about. So, and then once we figure out what type of piece of equipment we have, then we can look at the near boiler piping details and the things that are in around there that will make sense. Then we look at supply and return piping for both the boiler as well as the supply and return out to, let's say, manifolds, or a series out to baseboard runs or something along those lines. And then we got all the hydronic specialty stuff like expansion tanks and zone valves and air separators and all the stuff that goes in and around the heating equipment. But last on this little pyramid here, of course, is the circulator. In order to size the circulator correctly, we need to know all this stuff. Now we're not going to cover everything today, but I've got it kind of shortened up to a point where you can see how this process would take. This is kind of the slide I used to start a full day training course. So, we're not going to cover all this stuff. We're going to cover quite a bit, and we're going to hit the points that have to do with circulator sizing for the most part. So, the first fundamental thing we need to know is, well, two things here. In this case, we need to know what the gallons per minute is, and then we need to know at that gallons per minute, what's the resistance or the friction or the feet of head that the circulator is going to experience? And we'll go through that one thing at a time. We'll start with GPM because the GPM is based on the load. Okay, and so that load will be what drives this GPM. We'll show you what that calculation looks like. Okay. Since I said everything starts with a load, let's just understand that that's your bullseye on a target. You could you could use the bullseye, or you could use the shotgun approach. And which one's going to be a little smarter? I think you know the answer to that. So we want to try to figure it out. There's all kinds of ways to do a heat loss calculation. One of them that we do is the first hour of our full day session typically is to show you how to do it by hand. But nowadays, everybody's got some kind of software out there that will help you do this job quicker. It's not any better. I can do a really good job here by hand, or I can do it with a machine. The machines are typically faster. But again, garbage in, garbage out. We got to know what we're doing, and that's why we still do heat loss as the first part of the class. We'll do it manually and just show you how that can still be done. Here's just an idea of what one of those heat losses might look like. We start with a room by room heat loss. We got the infiltration, we got windows, walls, ceilings, we got doors, things like that. Finally, the floor. And we're in seminar land, so we make our numbers nice and round. But let's say this one room is 4,500 BTUs an hour. Then we do the other rooms in the house for a total of 50,000 BTUs. That's going to be our bullseye on our target. That's what we're shooting for. So anyway, just understand this is just a fundamental starting of everything that we do in the world of heating or cooling or anything. We need to know what the load is. Okay, we'll start with this hydronic calculation, and it's a dual conversion formula, and we call it the universal hydronic formula. I'm not sure what everybody else calls it, but I think between a couple different companies I've worked for, we've made that pretty much known. That's what it is. But I like to go a little deeper and say, hey, it's a dual conversion formula as well. And this is what this next couple of slides will talk about. If we're solving for gallons per minute, okay, this is what we're solving for, equals, right? But it's based on the load that's a British thermal units, right? So BTUs and GPM, they have something that correlates, but they're two different things. And this is what I want you to understand. Gallons per minute is what we're solving for, but it's based on something that's a British thermal unit. Now, let's go back and remember what a British thermal unit was. It was the amount of energy it took to raise 1 pound of water 1 degree Fahrenheit. Okay, nothing to do with gallons. So that's part of the conversion, right? We need to take pounds and turn them into gallons. And that's part one of the dual conversion. The other thing is a little easier. Is notice it's British thermal units per hour, but we're solving for something that is based on minutes. So understand that difference as well. And there's your dual conversion. Now, the temperature differential is always needed to know to come up with this number. It's part of the calculation, as you can see. And we take that delta T and we times it by a constant. And I'm going to use 500 now, but we're going to explain what 500 is and where it comes from and when it's not 500, because it's not always 500. So now let's break it down a little bit more. This is like an extended view of this same calculation, where we're talking about the density of the fluid times 60 minutes in an hour times the specific heat. If you remember what I said a BTU was, that kind of describes it right down here. What is a British thermal unit, right? That's a specific heat of the fluid that we happen to be using. And this would show down here, it would be for water, good old H2O. And then times again by the temperature differential, or delta T, of the fluid during a designed condition. We call it design delta T of the fluid. So now I will make a point here that notice you don't see 500 in there right now, because the constant, the number that we're going to use, is derived from the density and the 60 minutes in an hour conversion and the specific heat. And that's what we're going to show you the breakdown of. And I'm going to move kind of fast. I should have said, I told a couple of folks before we got started that there are some handouts that go along with this, and that'll be a follow-up email to you, or local correspondence there with Northwest Pipe. So anyway, other things that we need to know. Okay, remember we needed to know the GPM and the feet ahead. We also need about the fluid itself. We need to know what the composition is. You know, what is it made of? How much glycol's in it? Or is it just good old water or things like that? Some of the ground source heat pump people have been mixing some other things together, and those will have some differences that need to be accounted for. And we need to know what the temperature is, and you'll see why when I show you some of these charts and lookup tables and stuff, because we need to know what the temperature is, because it does affect, and you'll see that. Let's start with the basics here. I want to describe what you're looking at. You're looking at a cubic foot. It's an increment. That's 1 inch, or excuse me, 1 foot by 1 foot by 1 foot cube, and it's full of something. In this case, it looks like it's full of air, and it would be if we were doing, you know, the HVAC stuff where we're moving cubic feet per minute. But that increment is also part of what we do in the world of water or hydronics. Okay, you'll see this is a chart I found from Engineering Toolbox, just because I didn't want to rewrite it myself, and I'm taking the lazy way. But notice it's kind of hard to find nowadays. It's in Fahrenheit, okay, in this column here, and then that's how much that cubic foot of fluid weighs at the associated temperature here, okay? And then over here, they've actually broken it down for us in North America to US gallons. But I want to use this to make a couple points. The first thing is, since we're dealing with sizing circulators based on US gallons, then we got to figure out how many gallons are in a cubic foot, and they've done that for us. But let's not forget the math. There's 7.48 US gallons in a cubic foot, okay? So that's what they've done here. If you take this number right here and you divide it out by 7.48, you'll get this number. So it just tells you how much weight there is, okay? Notice what they've done to get this. Now, when you take that number and times it by 60 minutes in an hour, that's where you get the number 500. So those are watching, you know, it doesn't hurt. Everybody's got a cell phone nowadays that's got a calculator on it. I'll just encourage you to feel free to go ahead and do these calculations, okay, with me, because this is how you get comfortable in doing these things. Is not just to listen to me, but actually start to practice and doing it yourself. And this will be part of your handout. You look down here, you can see class handouts. You'll get a copy of this so you can refer to it later. Let's do something. I'll say this. I'll try to give you shortcuts. Whenever there's a shortcut applicable, I'll give you a shortcut. But I want you to know the longhand version of it as well. Then you can use the shortcut and still be able to explain to somebody why and what the difference is. Now, if I took the number 60 minutes in an hour and I divided it by 7.48, it gives me another constant that I can use against the weight of the fluid in per cubic foot. And you'll see this a lot, like in Siegenthaler's books and stuff. He'll just show this, and he just says this constant is based on the units that we're using, but never gets into a big explanation of it. But I'm just telling you, all it is 60 divided by 7.48. So now I can take over here at 140 degrees, I can take this 61.38 times 8.02 and carry it all the way over here. You'll see I get 492. And then let's go up to hotter fluid if we were using 180 and doing either the longhand or the shorthand version. You'll see that turns out to be 486. Now, what I want you to look at is 500, 492, 486. Look at what the number's actually doing. It's reducing its value. Look what happens when we talk about glycol, right? A 30% propylene glycol mix at 140 degrees is 477. And then if I do a 40%, it's 465. And if I do the good old, college try 50%, it's 450 basically, 449, 450. So again, that number is digressing. It's going down, and it's counterintuitive. You'll see that in the full calculation, the lower this number is, the end result is slightly higher flow to compensate for the fact that that particular blend and at that particular temperature doesn't have the ability to carry fluid and carry energy and distribute it as easy as good old water does. Okay. Anyway, so we're going to try to answer this question. Okay? This will be another one of your handouts, but it's talking about the density of fluids. Okay, again in pounds. So always let's figure out what our temperature is. You can see over here what is the mixture, and it also has no mixture, so you can compare with water as well. It's a handy little lookup. I got this from Dow. You use whichever brand glycol you folks are using. They'll typically have the same type of lookup columns, or they'll have it in an app, or they'll have some way of getting there. But first thing we need to do is solve for the density. So we just put the temperatures in there. We put the mixtures in there. I'm using 40% for now. And I see that a cubic foot of that product at that temperature weighs 63.27 pounds. Now, here's a longhand version. I take that 63.27 divided by 7.48 because that's how many US gallons are in that cubic foot. And it tells me that 1 US gallon of that product now weighs 8.46. Okay. It's a longhand version of doing it. And then we take that result here and we times it by the specific heat, which will be another lookup table we're going to go to next. And as a reminder, feel free to turn your mics on and interrupt me at any time. Otherwise, I'll just babble on. So let's use the same for consistency's sake, 140, and over here at 40%. And this number here, what do we do with that? Well, that's an actual deduct, okay? We take that 8.46 from the previous slide, and we get a deduct of almost 10%. That puts us back at 7.75 times 60 minutes in an hour. That's why 40% propylene glycol at 140 degrees, we'd use a constant of 465. Everybody okay with that? Let's talk about a couple things. I want to go through this. I think I've covered this with you folks before. This is just an eyebrow raiser usually. And just to make it a little quicker, and I won't expound as much as I normally do, but generally speaking, most of your glycols will come based on their protection rating in two different columns. One of them is freeze and one of them is burst. For the most part, in the HVAC world, we use the burst column. We don't worry about the freeze column. The freeze column is for things like a normal application where you're running really cold fluids. For instance, under a design condition, I normally am pumping minus 30-degree fluid. Okay, if I wanted to do that and not have any ice crystals show up, hence the name freeze, then I would need 52.4% Dalfrost mixture or propylene glycol mixture. That would keep that from happening. That means all day long I could pump minus 30-degree product. Okay, that's not typically what we do under a design condition. Remember what a design condition is. It's the condition at which the system would be fully up and operational and going to beat the band. For instance, the boiler is approaching its maximum firing rate. The pump is up to its maximum speed. The fluid temperature is up at a design condition, etc. Okay. Now look over here. If I were just worried about the fluid actually expanding to the point of bursting my pipes or my heat exchanger or something like that, I really only need about 35% mixture. Okay, so, and look down here, this looks like a typo, right? This looks like a typo down here, just repetitive numbers. Well, In reality, you never need more than 36.6% glycol if you're worried about bursting your pipes, that sort of thing. So anyway, just a heads up on that. And that's not part of your handouts. I want you to refer to the manufacturer glycol that you use. Again, I use this from Dow because they're fairly generic. A lot of the manufacturers that sell glycol might buy their base product from Dow as a chemical company. I'm not saying that for sure, but some of them do. So since everything starts with a load, let's go back to this, right? 50,000 BTUs. We're going back to what our target was, right? And let's do the calculation so you can put all the blanks in here. So our example was 50,000. 50,000 is going to go up here, okay? We used water, 40% propylene glycol at 140 degrees. That's where we got this 465. And here's how the calculation longhand works. Notice down here we would have brackets, so we're going to do that calculation first. 465 times 15. 15 in this case was my delta T, or my temperature differential that I was going to use for that particular job and that particular application. Let me expound a little bit on delta T. A lot of people think that it's always 20 or it's always 10, or it's not. It's a variable. The delta T will change typically based on what you're doing with the heat emitter. What type of heat emitter is it? And that'll normally drive your delta T. And that applies to radiant floor, panel radiators, baseboard, fan coil units, all kinds of things. So typically, and I'm trying to use some oddball numbers just so you don't get used to just using one number. Okay, so if I take 465 times 15, I'm going to fill that in here at 6975. So 6975 is what's here. 50,000 BTUs is what's here. So if I take 50,000 BTUs divided by 6975, I get 7.2 gallons a minute. Now that's the longhand version. Let me show you a shortcut. You take your load divided by your constant, divided again by your delta T, because the division and the multiplication are reciprocals. And so this is why this still works. 50,000 divided by 465 divided by 15-degree delta T is still 7.2. So again, I'll give you shortcuts when they're applicable, but I want you to remember the longhand version and why things are like they are. So this whole time we just spent 20 minutes talking about how to get the first part of the pump calculation, which is GPM. And once you get your arms around it, it goes much faster. Okay. Any questions? All right. Silence is compliance.
What different heat emitters do you use different delta T's for, and why?
Oh, good point. Well, let's say for instance, let's use radiant floor. Radiant floor, if we're going with a real easy layout pattern, we'll call that single wall or double wall serpentine, where you just go out to the outside wall and you tighten up your spacing a little bit, and then you come back to a wider spacing and you work your way back out. Generally speaking, what we're trying to not have is a really big floor surface temperature profile change. So in order to correct that, one way is to tighten up the delta T from say a 20 to a 10, and that will give me a nicer floor surface temperature profile than it would if I just left it at a wider delta T. So there's one example. But I also have to remind everybody, you can also change your layout pattern and still achieve roughly the same thing. If I went to, either a serpentine counterflow or a spiral counterflow layout pattern, I could still achieve a fairly even floor surface temperature profile in lieu of doubling the GPM number. Because when we go from a 20 to a 10, we double the GPM requirement. So good question. I appreciate that. Hopefully that answers.
For I guess for a bit, but do you have I guess a slideshow or something that I could keep to show my guys as to the radiant versus say copper fin baseboard versus radiators. You know, that quite often I go and use a larger Delta T going through my boiler, for instance. And like you
Yep.
said, everybody assumes it's 20 for everything, which isn't the case. But it's nice to have something to show them what we do and why for some of these different
No,
scenarios.
yeah, it's a good question, and because us as TACO, because that covers so many other things that TACO doesn't really have anything to do with. I'll just say it, it won't be part of the handout, but let's look at a delta T's in 5-degree increments. Okay, typically the tightest I've seen anything that you would design for is about a 10. Unless we get into some domestic hot water recirculation when we're trying to keep the average water temperature up higher than a certain number, we might tighten that up to, I've probably seen it about as tight as a 5, but that's rare. And that's mostly commercial, and it's all around Legionella mitigation and some other things. So don't take that one and run with it. So let's start at 10. And let's say 10s would be like I already described for radiant floor when they're the lazy man layout method, which would be your single wall serpentine applications. 15 would be out there for another radiant application where I might have some single wall serpentine and some counterflow spiral in the same loop configuration, and that can be done as well. You know, again, tighter spacing on the outside and then get to the spiral toward the middle. I've seen that done. 20 would be lots of things, some radiant with counterflow spiral, counterflow serpentine. 20 would also be a lot of fin tube baseboard, depending on how many emitters are on the same run, that sort of thing. Okay. 20 would be just what they've used for years and years as a standard, a high temperature, 180, coming back at 160 kind of design criteria. When we get into condensing pieces of equipment, well, before I do that, let's talk about panel radiators. Oftentimes those, and should be in a lot of cases, depending on what you're using to build the system, but all day long, people have used 30-degree delta T's for panel rads. And a lot of that is driven by again, the way that they're piped up. Are we using small tubing to get out, and we're doing home run systems, kind of like Siegenthaler has shown for zoning back at the manifold and those sort of things. And the smaller pipe's going to, not allow you to do real tight delta T's. The other thing I'll point out is panel rads are primarily used in Europe. And we see that as a standard everyday heating system, hydronic heating system over there. And all day long, they're designing those at a 20-degree delta T, but their 20-degree delta T is Celsius. Okay, so that to us folks in North America, that's 36 degrees Fahrenheit. So again, don't worry about doing panel rads at 30 degrees. The folks across the pond are doing it at 36 all day long, have been quite successful with it. So anyway, hope that helps. So we already covered the load. Okay, what's next? Well, we got to figure the feet ahead and pressure drop. So these next few slides will talk about that. And we'll talk about pipe sizing. Okay, just understand that we can run the water too slow and too fast. Okay, too slow, we got some issues with potential airlock. If you got air in there, you got some noise involved there. And if I lock up, I get no heat. Okay. Too fast is a little more intuitive. It just says, hey, I could potentially run the fluid so fast that I could eat the pipes up, okay? And I can hear the rushing sound of the water inside the pipe, and that's never a good thing, right? If we had more time, I'd do some more examples, but just understand generally speaking, you should never be able to hear the fluid running through the pipe in a closed loop heating or cooling application. That means if you can, your velocities are probably way too high. And that's what this next few slides will build on, okay? Kind of the rules here is stay less than 4 feet per second and stay above 2 feet per second. So 4 feet per second and 2 feet per second. Remember, that's based on how fast the fluid's moving through the water's moving through the pipe itself. Okay, so we'll look at that as a speed limit. There's another rule out there that ASHRAE talks about, and most of the people that deal with the mechanical engineering firms and stuff, they just use this number because it works both ways for them. Okay, excuse me. The 4 foot and the 2 foot kind of comes from modern hydronics and from Siegenthaler and people that prescribe up to about 1.5 inches. And then from 2 inch and bigger, they just say, hey, you know, and I'll show you why here in a second, but let's just use the 4 foot of head per 100 foot of pipe. And that works well. And what this means, let me explain it because sometimes it doesn't make sense to everybody. What we're saying here is that the resulting pressure drop, if I ran a certain gallon a minute through that size of pipe, would be 4 foot of head. Okay, so again, it's the resultant pressure drop based on that type of pipe, based on that size of pipe, and based on the GPM running through it. So it's not as intuitive, but it is for the engineering community, and I'll show you how to interpret both of those. Here's one of them showing those. Okay, I call this the pipe sizing maximums. Excuse me, this will be part of your handouts. And it's always got to be based on a particular type and size of pipe. So this left column that I'm using to teach here is just type L copper. Okay, this would cover you for type M as well because it has a smaller diameter. Excuse me, the type L has a smaller diameter than the type M. So the resultant pressure drop would be a little less. So maximum GPM at 4 foot of head per 100 foot of pipe. Okay. So for instance, if I had a piece of 1 inch type L copper and I ran 7.5 gallons a minute through it, notice this is the reference, then the result of that would be 4 foot of head. Okay. Now the other one over here is 4 feet per second. This talks about how quickly the fluid's moving through the pipe. Let's stay with 1 inch here. 1 inch, I could push it all the way out to 10 gallons a minute because at 10 gallons a minute, I would be at a speed of 4 feet per second, or better said, a velocity of 4 feet per second. Hopefully that makes sense. Always read the fine notes down here. If you use the maximums, gives you no wiggle room. Okay. What I'd like to say is, if you need to use, for instance, 10 gallons a minute for this piece of 1 inch pipe, make sure that 1 inch pipe is nice and short. Because what you'll find is if that run is all the way across the building and back, by maxing out the velocity, the end result will be a whole lot of pressure drop. So you will be using the proverbial Baosfac. You know, what's a Baosfac? That's a big ass one size fits all circulator. And everybody knows that those are generally R0013 or Grundfos's 2699, et cetera, et cetera. And what we want to try to do is design our systems at smaller circulator sizes, so the end user, the building owner, doesn't experience the additional expenses that are involved in that. So anyway, so let's move on. Again, I talked about this in ranges, right? So the ranges go to 1.5 inches, typically stay with the 4 feet per second and 2 feet per second rule. And when you get over to 2 inch, 2.5, 3, 4, all the way up from there, that typically commercial. This is your ASHRAE number. This is your modern hydronics number. So just think of it that way. Hope that helps. Here's another version of that same thing. It's a maximum velocities chart, but over here in red, I have type M copper. Here in blue, I have type L copper. Over here in green, I have SDR9 PEX. Okay, so SDR9 is our standard dimension ratio. So anything that we're using nowadays in North America tends to be SDR9. That has to do with the wall thickness. Okay. Same caveat down here though. So part of your handouts. Again, look at this one. This is a little different. Notice I didn't give you the ASHRAE number. This is just kind of modern hydronic stuff. But what I wanted to use this for is a quick lookup to say, hey, if I had a piece of 1 inch type L copper, I could keep it above 5 foot or above and 10 or below. So I like to look at it in here. Anything between 5 and 10, you're in the sweet spot. You're good. You're not going to blow either of those rules. So either meaning, excuse me, 4 feet per second or 2 feet per second. You're going to stay right in between those two. The other thing I wanted to show is this delta T thing. Remember, we were just talking about that. So, at a 10-degree delta T, a 15, a 20, etc., what these numbers are is to let you know. Let's give another example. At a 30-degree delta T, I could do a boiler header, the primary portion of a condensing boiler. I could, if I ran 10 gallons a minute through that 1 inch, I could deliver almost 150,000 BTUs at a 30 degree. What that might mean is the boiler primary piping might be 1 inch because it's relatively short, but my secondary header might be 1.25 inches. Okay, so just kind of to keep that in mind. Where can I save money? Well, by being smart, by sharpening my pencil, by dotting the I, crossing the T, and that's where these little quick lookup columns will help you out. And again, this is something I've used years before I even was working with Taco. It's not anything that's based on Taco. It's just general rules within our industry. So use it if you want to. Okay. What I did here is I just wrote in those the ASHRAE rules. Okay, the 4 foot ahead per 100 foot rule is right next to here, because when you get up into these bigger sizes, you can save yourself some money by not trying to look for 5-inch pipe because you had 200 gallon minute requirement. You know what I'm saying? So you can go up to 270 and still be at 4 foot ahead per 100 foot, and that's an accepted ASHRAE standard. All right, so now you heard me talk about estimates versus calculations. I'm going to go pretty fast through this. This is the kind of stuff you'd get at a boiler class when they get to their pump sizing segment. I always cringe a little bit because I've been guilty. I've been on both sides of that arena, and so I want to talk a little bit more about not oversizing a pump. When you do these estimates, they tend to oversize. So the first oversizing here is you take the total measured run of the first zone and you times it by 1.5. That means you're adding 50% valve and fitting factor. And guess what? That's 50% is a big fudge factor typically, and not in every case, but in most cases it tends to oversize. Now I'll show you another thing that oversizes is to use the 4 foot ahead per 100 foot of pipe. Gives the assumption that you're maxing out the flow of that particular size pipe. Okay, so anyway, what we're saying here is you take this measured run. I'll do an example here. You times it by 1.5, then you times it by 0.04, and then you get your result. Let's say we measured 150. We take that times 1.5, that gives us 225 times 0.04, and the guess, and by golly, is 9 foot ahead. Well, again, you can use that just as an estimate, but don't use it for actual pump sizing. It tends to oversize things pretty bad, actually. So here's another shortcut I'll show you. You can just take the 150 times 0.06. It'll give you the same number, because if you take 1.5 times 0.04, it's 0.06. Okay. Again, estimates only. Let's show you the calculation that a piece of software would use. You folks that are using anybody's software, let's say Radiant, because that's the most popular, and at the end of the design summary it says you have this many feet ahead. Well, it's taking this information in consideration. We're solving for the head, and it's that's what we're solving for, head loss. Okay. And we have this K number, we have this times C number times L number times this thing in brackets here. So let's real quickly, we're not going to do this. I'm just explaining what's in the background to the software that you're using, so you have a better idea of how it's coming up with this number. This K factor is based on things that we've already talked about. What type of pipe is it? And what size pipe is it, so that we can figure out what the ID is. Now, not only the ID, because we have different types of pipe, we have different roughness factors that are built into this K number. Okay, so that's what That's why those pieces of software ask you those kind of questions, okay? We're going to take that, and that's just a number that's on a lookup table. Then we take that number, we times it by the C, which stands for your correction factor, which we've already talked about as well. We talked about what the temperature and the mixture of the fluid is. So that's my correction factors. Again, that's a number, and we'll times that by the total developed length. So this is assuming that you've already given an equivalency to the straight pipe as well as the fittings and valves and all that stuff. And then finally, you times it by the flow, which is what the F stands for, the flow to the power of 1.75. Now, when you do that, that's going to give you a real accurate look at what the pressure drop is. And that's, it's easy for computers to do. It's just a spreadsheet that's hiding in behind there. It's kind of an algorithm that it uses, okay? But if you're doing this by hand all the time and look up tables and everything, it can kind of be a headache. So let's look at the calculations the easy way. This is, I found, is pretty accurate as well, and a lot of other people use this. And I will give you a little background though, and give some kudos to a certain individual that's working on some of this. But again, we take the total measured run, and we'll use the same number, 150 foot, and then we'll do an estimate of the valves, the T's, the elbows, anything that's used in there. We'll use these equivalency charts. Okay, an equivalency chart will tell you an approximation, and I'll explain approximation here in a second, of how much pressure drop that particular fitting or valve or whatever it is would impart on the fluid running through it. Okay, and of course we use these charts, and then we tally it all up at the bottom. We're going to do an example so it'll make sense to you. Okay. So let's show, this is just like a wall hung Mod Cod closely spaced T, so that we'll call that our primary secondary configuration. I like to say T's butted together. But let's look at zone 1 at 3 gallons a minute, zone 2 at 2.2, and zone 3 at 2. And these GPM numbers came from the loads based on those zones. Okay, so these are in this case hypothetical. But let's start with zone 1. And what we're saying here is we're going to measure from the outlet side of the pump, and we're starting to start counting things. We got a check valve, we got a ball valve, we got a T on the run, T on the run, T on the branch, ball valve, zone valve, and pipe valves. Everything that's out here, we come back over here. We got a globe valve, we got a ball valve, we got a T on the branch. Come back over here, we got a magnetic dirt separator, T on its back, or on the run, I should say. T on the run as well, ball valve, air separator, okay, back to a ball valve, and now we're at the inlet side of the pump. That's what we're trying to measure when we get that 150 foot, and the equivalency of the valves and everything, okay? Now let's talk about some of those equivalency numbers. Now I was over a few months ago at this gentleman's house, and he actually has this book, and I'll tell you who he is in just a second. Maybe some of you already know him, but Experiments Upon the Flow of Water in Pipes and Fittings, and I'll show you the other page over here. Again, look at this. Look at the date on this thing. When you look at the equivalency charts that are out there, and the ones that we're going to show you, a lot of that stuff is derived from information back from before the turn of the century by this gentleman here. And he had one of his heirs expounding on this at a later time. This particular gentleman, Gary Klein, has this book. I was over there, and he showed it to me, and that's why I took a couple pages and told him I would let people know kind of what his work is. Well, what he's doing currently, he's only going up to about 3/4. I think he's working on 1 inch. But so say for instance, I had 1/4 inch flexible pipe, I had 3/8 flexible pipe or copper, and I had 1/2 inch and 3/4, etc. He's gone through and actually tested at the various velocities, 2, 4, 6, 8, 10 feet per second, and he will be able to tell us what the actual PSI is in resistance at those given flows. Okay, I'm pretty sure he's only doing water because primarily his goal is plumbing and pressure drop and things like that. But that's some really good information. I'm just giving you a little background on where these equivalency charts come from, like I'm showing you now. Okay, so we're going to go with a 3/4 inch based on the flow that we were using, which was 3 gallons a minute. And so we're going to shade all this out, and we just start tallying things up. We just start counting things: check valves, T's, T's on the branch, T's on the run, etc. Ball valves, globe valves, anything that was in there should have been some zone valves, etc. Anyway, I add all this stuff up in there, and I get a total fittings equivalency of 70 feet of additional straight pipe. So that's where people lose this whole equivalency thing. They can't get their arms around it. It's just as if we had 70 more foot on that 150-foot run like I'm showing you here. So we're still roughly what we were using the valve and fitting factor, but with some difference. And this is what the difference is. Now notice, I had 3 gallons a minute. I'm just showing somebody's PEX pressure drop calculation. So I'm going to use 3. I'm going to come over here to 3/4 inch. And if I ran 3 gallons a minute through, there's my 3 gallons a minute, through a piece of 3/4 inch PEX. And remember, PEX is, because it's a flexible piping system, is more affected by the temperature of the fluid running through it. So it actually relaxes a little bit the hotter that it gets, and the pressure drop is slightly less. Okay. So just remember, there's a temperature contingency on flexible piping systems, and the manufacturer of the product will give that to you. Okay. So 2 psi per 100 foot of tube, or I like to do it this way, 0.02 psi per linear foot. That keeps you from fractionalizing the 100-foot number. So I just take everything back to per foot, and then I times it by the total number of feet. It's just it's the way I like to do it. You could do it either way. As I'm going to show you now, here's from the Copper Development Association. Here's 3 gallons a minute through a piece of 3/4 type M, and that tells me what the pressure drop is in psi per linear foot of tube. Okay, per linear foot is my multiplier, or 0.9 per 100 foot. So that way you just pick and choose which way you like to do it. Many people like the 100-foot increment. I prefer the per foot because it's easier for my brain to not have to fractionalize things. So, all right, so let's do that math together. I'm using the copper number. Okay, 220 times 0.009 gives me 2 psi. We always got to convert psi to feet ahead with this number right here, 2.31. So 2 psi times 2.31, we can assume we'll have about 4.6 feet of head on that particular run if it was just water. What if I had propylene glycol at 140 degrees? Well, there again, that's about 25% more additional, I should say, additional pressure drop, and so you have to count for that. So you're going to be closer to 6 foot ahead with a glycol. Just remember, the viscosity of the fluid affects the circulator's ability to pump. So that's why you got to make sure. Now, if you can recall, I talked about one of the algorithm numbers that accounts for this, right? Actually, it was 2 of them. One was temperature and was my correction factor for my my fluid temperature, and what's the mixture. All right. So anyway, it's just a little, it's closer to reality. Even though the information that we're using for equivalencies is relatively old, it's still, it's been my experience to be more accurate than just throwing a random valve and fitting factor. Guess what, folks? Valve and fitting factors are nothing more than WAGs. And if you know what a WAG is, figure it out. Okay. So again, and what's crazy, and I don't think it's crazy, it's just path of least resistance. A whole bunch of people use these WAG numbers just because it's worked for them. Again, my experience has shown that they tend to be oversizing quite a bit, a lot of times by double. Okay. Pressure drop cumulative. Let's carry on with this, and we'll take a little break coming up. Just showing you with that same arrangement, zone 1, zone 2 and zone 3. What I'm going to show you is a mistake not to make. Okay. Here's those zones just laid out. Maybe somebody scratched this down and they were going to do a calculation, and they make this mistake. Okay, they take this column and they add it together, and they should. But because they're taking this tally and this column and adding it, they do the same thing over here, and they make a mistake. Now, you folks that know this, hold on to it. That's not what you're supposed to do. Okay, that leads to pump oversizing, and where we're going with this is you do not, when things are piped in parallel like they would on a manifold like that, well, you don't add the head together. It is not cumulative. Okay, so all you do is you remember to use the higher number of the three. In this case, 3-zone system. Could be 7-zone system. You would take the higher number, and then any incidental pipe valves and fittings in and around the near boiler piping, right? And then you add those numbers together. And this is why, okay? If I had a pump here, it's in the off position, I'm pumping out, it's an open system, okay? I'm using this just to explain. Same thing applies to closed loop. If I had atmospheric pressure on this, I'll seek liquid level here. You could see I'm level. If I turn the circulator on, then I'm going to pull this down and I'm going to push these up. As you can see, these columns full of water are being pushed up. Now, this is pretty intuitive at this point in time. If I have the ability to push up to 10 foot of head and spill water out this column, I'm also spilling water out of the 5 foot and the 7 foot as well. So I don't need to concern myself with any more head than the worst case. Hopefully that helps. That, a picture's worth 1,000 words, and you might have seen this before and just not got your arms around it. That's why I drew it up. I used to draw this on a blackboard, but it's just easier to show it this way. So hopefully that makes sense, and will help you understand why you only use the worst case of a parallel pipe system. So again, we take the worst case and the any other incidental flow that's in near to the boiler, and we come up with 7.2 at 7. More correct. It's let's show you how to use that. 7.2 gallons a minute, 7 foot ahead. There's 7 and a little bit, and then there's our 7 foot ahead. Come over here, and that becomes my duty point. Okay. My duty point would be where it's going to operate at something less than maximum speed. When we talk about something at maximum speed, we call that the operation point. Okay, my duty point's down here. That's the duty means what does it need to do under that design condition that is specific to that job. Okay, and hopefully that helps out. So that would be the duty point or the operating point if it slid all the way up here. This thing here is our system curve, and we're going to talk about that next. Okay. Well, we're going to talk about in the next segment. I think CV clarification, I'm just going to wrap this up in the next 5 minutes, just reminding you what the CV is all about. CV stands for the flow coefficient, or it's a shortened abbreviation, not really abbreviation, just CV. Some people have tried to say coefficient of velocity or something like that. I've never found any other thing to tell me what it is other than what we call flow coefficient, the coefficient. Okay, coefficient meaning just what's the number of that particular device when it was tested. Again, we put these things on test benches and we impart enough flow through the device until we get to 1 psi, and that tells us what the actual flow coefficient is. We use that as a benchmark. It's just an industry benchmark, so I can take, for instance, a TACO zone valve, and I can compare it against another competitor and see which one has less resistance, or which one's going to impart the least amount of friction loss to the circulator that has to pump through it. Normally, a higher number in a two-way valve like this is a good thing. For instance, this Zone Century 3/4 inch sweat version of it has a CV of 10.3. That means I could pump 10.3 gallons a minute through that thing, and I would only have 1 psi or 2.31 feet of head by that flow going through it. Okay. So again, this gives you a visual of the same thing. So if I'm sitting static, that means the pump's not running, no flow, just sitting there, and I got 15 pounds on each side of this valve. And all of a sudden I can, on the test bench, I can turn up my GPM incrementally up until I get to the point where I see 1 PSI. Then I look down here and see what GPM that is at a 1 PSI drop across the valve. That becomes the flow coefficient, or CV, of that particular valve. Hopefully that helps explain it, and hopefully, instead of just throwing your arms up, that will help you understand, especially when we start building that into calculations. So when we solve for that, let's show you how this is used in a calculation. If we're solving for head, we do that by figuring out what the GPM that we're going to run through the device. Here's the device's CV listed CV, okay? And then we square that. That squaring gives us the PSI drop, and we convert that to feet of head. Here's an example. 5 gallons a minute shoved through a device that has a CV of 1.89 is 2.65. Times itself, where we square it, is 7 PSI. 7 PSI times 2.31 is 16 feet of head. So again, this is how we use the CV to figure out how it's going to impact the circulator performance within a particular system. So hopefully that helps as well. We're not going to have time to wrap this up, but all I'm doing is expounding on what I've already just said. Just remember, the CV does impact the pump sizing, and I'll throw one thing out there. The actual pressure drop of the valve itself, when we're doing mixing valves like I'm showing you here, is a 2-way, here's a 3-way valve, here's a 4-way valve. The pressure drop of that valve on a particular system is and can be anywhere between 30 to 50% of the total pressure drop of that particular zone. So just kind of use that, put that in the back of your head, or make a note of it or something. When we do that, when we push that from 30, 35, 40% of the actual pressure drop of the entire zone that pump's responsible for, we get really good valve authority. Okay, we get that valve to operate more correctly. The problem that we see with valves is them not so much being undersized, but often they're oversized because they're not using that principle I just told you about. So, any questions?
Why is the CV value on your 3/4 inch Century greater than the 1 inch?
That's a great question. The actual ball size is the same within the 1 inch as it is the 3/4. And the Venturi effect of the reduction in going from 1 inch to 3/4 inch creates a little more turbulence. Imagine a Venturi in your mind. It's creating a little bit more turbulence and therefore a little bit higher pressure drop.
So why wouldn't you guys make it with a larger ball?
It's another thing to get molded. It's another. Here's the good thing about it. The 1 inch, and I'm not looking at it right now. The 1 inch valve probably has a CV of somewhere around 7 or 8.
Yeah, I think it's 7.3.
Okay, that's still well within the flow that you would run through the 1 inch pipe. See, 1 inch pipe is going to be somewhere, I think, 7.5 up to 10. So if I'm in there around 7 or 8 in what we're saying the CV is, that's about what I'd be running anyway. So it's still it's not bad. And in a zone valve, it's just open and close. It doesn't mean that much. But there might be times in a situation where I would want to run a 3/4 inch valve within a 1 inch application for that valve authority. And that's why we also have this valve, for instance, we have that with 1 inch unions that has a 4.5 CV, and so does the 3/4 inch. So that gives the guy the flexibility to not having to increase back up to 1 inch using a smaller valve. He could use the same valve if the dollars aren't the same, but he might weigh that out and say that that's what I want. So just
But that
based on
one's only
time.
a 4.5.
4.5 on the Union style in both the 1 inch and the valve I'm pointing at right now. This is an eye valve, right? It could be used for mixing or set point and that sort of thing, or outdoor reset, that sort of thing. So let's do a little break. Okay, we said we would do this. I'm going to leave everything on. I'm going to switch gears a little bit in my presentation, but let's come back in 5 minutes. So what are we at? Roughly 7 after. We'll come back and start the next session. Everybody good with that?
Perfect.
Okay, let's plan on it. All right, let's go ahead and get started. Hopefully everybody can still hear me. And I'll say hi again. See me? I'm going to shut that camera off. Somebody interrupt if you don't want to get started. Okay. Otherwise, I'm going to jump in. So this session, circulator facts, curves, selection, where they belong and why. Okay. So people are still getting this thing wrong, right? They're not understanding some of these fundamental things that that are still out there. So we're going to, cover things like terms like head, what it really means. Some people are misusing it. Understanding and getting your arms around what the hydraulics of the system are. Yeah, we're in the hydronic business, but it's all about hydraulics. Okay, mechanical energy, what it is, and does it show up in our system? The point of no pressure change, people still getting this wrong. So this has to do a lot with just system design, or the guy that's out servicing the system. I should say guy or gal that's out there. There's some great female service techs out there, and they're coming up and they're doing well within this industry. Uh, curves. What is a curve? Some people are getting things confused talking about curves. So there's, generally speaking, within our world, there is 3 different types of curves, and we'll make sure you understand what those are. Centrifugal pump, right? Centrifugal pump. Circulator, not a pump. Again, it's synonymous. If I say pump, I mean circulator. If I say circulator, some people will think it's a pump. It's generally what we use at TACO is anything under 1 horsepower we call a circulator, and anything over 1 horsepower we call a pump. And it kind of follows the guidelines of what the Hydraulic Institute has put out, and Department of Energy. So again, we generally will say little circulators or big pumps. It's one way of looking at it, right? They use centrifugal force, right? Some people would argue to say, well, it's really should be classified as a rotodynamic pump. And it's like, okay, yeah, but the centrifugal falls within that scope. So, we just call them circulators, okay? And again, mechanical energy creates that differential pressure. We get enough and we get enough flow, and we do the job we're looking for. We got to have enough flow to do that. So anyway, here's my best Dr. Seuss here. It's a lean, mean, black and green pressure differential machine. Anybody recognize that character? Somehow or another, I got labeled who knows who that is? Anyway, you guys have got kids and watch that. So anyway, how is pressure added? Lorax, Chris got it. He had it figured out. So anyway, we use this example a lot, but imagine this little gal with a bucket perpetually full of water. It has a certain size hole in it, and she's running it around in a circle like this. Now, what I want to bring up is a couple things about it. You can imagine if that was full of water and it had a hole in it, and she was slinging it around in a circle like this, you're going to get a certain amount of water coming out of that certain size hole at a certain pressure, okay? Because of the centrifugal force, of course, okay? The same thing applies here. Remember what these were like before you had the safety bars on them. When I was a kid, they'd put some poor sucker up in the middle here, and we all get around it and sling it back and forth and just get it going as fast as they could till they fall off. So that's another example of what that centrifugal force is all about. Okay, here's a cutaway of a circulator. Okay, we call it the volute, or some people say casing, whichever way you want to call it. We're just showing you a cutaway of that. And we're showing you where the outlet side of it, some people say discharge, but some people don't like that word discharge. Here's the inlet portion of it, and some people will use suction, and some people don't like that name. So anyway, inlet, outlet, or suction discharge, whatever you feel like, okay? These little divider, like a little dividing gate here, or the vanes within the impeller. This is the impeller, and this is the eye of the impeller. You can see in this little dotted line, this is the continuation of the inlet portion. It comes up, through and in the eye, and then notice the direction of these arrows. It gets sling and or slapped to create this flow. A lot of people think it's actually scooping, but if you look at the way the impeller's designed and the direction of these arrows, it's slinging or slapping the water, and that's how it adds. As it gets up into this area here, that's how it adds that velocity and creates the mechanical energy that we talked about. Okay, that mechanical energy could be measured. And I want to show you here the difference between the outlet and the inlet. When we measure that difference, we can see exactly what the circulator is imparting on the fluid as far as additional pressure. Okay, we witness the mechanical energy by means of pressure gauges. Okay, so just not a play on words, but an understanding. We're adding mechanical energy to the fluid by means of the impeller actually spinning, creating centrifugal force. Okay. A couple other things I'll use as reference. The thicker the impeller, the more flow. Think of this thickness here as the ability to sling or slap more water than a thinner one. Okay, thin ones can't hold as much water. Thicker ones can hold more water. Therefore, the end result is generally more flow. Okay, we're showing you a couple different. Here's a closed-in impeller that shows those vanes. Okay, here's an opened-in impeller like a little 00 or older standard efficiency 00 impeller. Notice it's open. It's not capped on the top. This would still be down inside the casing or the volute, but this would be considered the eye, and then it's spinning in this direction. This one is spinning in this direction. Okay. So another thing to remember: the larger the diameter. Well, let me reference something real quick. The thicker the impeller, the more the flow. Remember the bucket analogy with the little girl spinning it? This would be akin to how big that hole is. Okay, this would be looking at the diameter would be how long was that rope at a given RPM. That little rope that she had on the bucket, if it got longer and she stayed at the same RPM, you would get higher pressure at that orifice at the bottom of that bucket. Okay, and nowadays when we're talking about the variable speed capability of these circulators, the high efficiency circulators, then we increase the speed or decrease the speed. We either get more or less flow and pressure at the same time. So just understand that's how those circulators are working. Okay. The other thing to get your arms around is understand, and I pointed this out, the whole thing about hydraulics, right? Imagine the fluid within the system all holding hands. It's kind of a kumbaya moment. Okay, they're all holding hands and they're all happy and they are connected. And I would like to also say maybe all of the fluid within a particular system becomes a macro molecule. Another way to get your arms around this is to look at all those as links in a chain. Okay. The reason I'm saying this is I want you to use this as an analogy of the fluid in a closed loop system. Say, for instance, this little link right here is moving this direction. Well, you know for a fact that all of the links in the chain are moving at that same time, right? So there's no hiccups. Unless I were have a break in the chain, I have no hiccups. The analogy I want there is that breaks in the chain or missing links are like air in the system. So that's one of the chief reasons why we got to get all the air out of the system. The initial purge first, and then high efficiency air elimination equipment like our Taco 4900, for instance. Okay. So let's look at the term head. You folks, if you've seen this presentation, I haven't changed it. There's a reason I'm putting head in quotations with this picture, and somebody can send me a little note if they know what I'm talking about. So don't use, this is the mistake that a lot of people make, right? They say that you have head pressure. Well, if I'm telling you that head means pressure, you wouldn't ever say pressure. So don't do that. And I'm guilty of, if I asked for a show of hands, mine would go up, right? Head pressure, right? No, it's head is pressure. And that's what I want you to think. When we're saying head, just get rid of the term head and say pressure. And understand, get your arms around that's what you're talking about, okay? Now, this is clarifying it a little more, and I've got some more pictures to go along to help you understand this. You've got to understand this in more ways than one to understand what we do in our industry. Okay, so in this case, John Barber came up with this, and I've kept it because I like the little cartoon configuration. But I am going to change some things. I'll show you some different pictures as well. What he's depicting here is a column of water 2.31 foot tall, and at the bottom of that column, he's got a gauge that has a pressure of 1 psi. Okay, that's what we're saying over here. It's roughly 28 inches or 2.31 feet. Okay. Another means of breaking this down is to take it to 1 foot increments. And a 1 foot increment has a column weight or pressure in this case of 0.4332. I've got lots of points on that, but that's basically, you could just say 0.43. But anyway, let's talk about just the term head again. You'll see terminology. People say static head, okay, and they'll use the term friction head, and they'll use the term pump head, okay, and all those are applicable within our industry, and you'll hear them used. And I just want you to understand what they mean by it. Just don't say head pressure, okay. So static head is the pressure, friction head is the pressure, and pump head is the amount of pressure, etc. Okay. Another thing about the hydraulics within the system has to kind of go with that links in the chain when I talked about air in the system and stuff. But if I have a closed loop system, if it's completely closed, I've got all the air out of it. The circulator has no responsibility in lifting the fluid. Okay, we don't care as far as the circulator sizing is concerned. We don't care how tall the house or the building is. Okay, remember, what goes up must come down. So everything coming down the other side of this Ferris wheel, say it's going this direction, we're not worried about lifting over here because the counterweight over here is helping it. It kind of neutralizes. So the only thing we need is a little circulator to get things going, and it just kind of goes, and it does a good job. Okay, so there's no lifting in a closed loop system like this. This is just showing you a quick little blow up of this. I think this was probably 4 or 5 years ago. In fact, this was Atlanta, and our big AHR show, some people recognize it as the ASHRAE show, will be in Atlanta again in February of next year. So hopefully we can see some of you folks down there. Anyway, circulator adds mechanical energy. Again, you're going to see it in the form of PSI. Notice in this scenario, the circulator is not running. As soon as I turn the pump on, now I can see the evidence of the mechanical energy that the circulator is adding to the fluid. Okay, now it's operating. I can see that I gained 4 PSI. Okay, and that's fairly typical of a small little circulator that's was sized appropriately and not the Benford 5000 that we talked about before. So anyway, what's a curve? Well, I'm going to just real quickly, I'm going to expound on each one of these, but just as a cover, we're going to talk about a circulator performance curve. We're going to show you what the difference is between that and a system curve. And we're going to say, don't be confused with this thing called a control curve. We'll get into all 3 of these. We'll be able to check those off. So again, feel free to interrupt me at any time. I'm moving right along here. So let's talk about circulator performance curve first. Here's an example of one. You folks have all seen this, but let's drill into it a little bit. We still have some people out there that aren't reading these curves right. They've got some misconceptions for whatever reason. So up here, we have the y-axis. That's the one that's vertical. And out here we have the x-axis, okay? Within that, we have feet of head and flow. Flow first and then feet of head. The reason I did it that way is you can't ever know what the resistance of the system is until you get a certain amount of flow. We get the letter Q will represent that in some cases, and that has to do, it goes back to an ancient language, but it's where we get the word quantity, okay? So I believe it's Latin. And then over here, head, okay, or height is a way to understand what H stands for as well. Okay. Now, here's that same column that's would be on the y-axis, and because of the increments that we use in our world, in North America anyway, we do everything in pounds per square inch. So I want you to get your arms around the fact that now, what if I had a square tube that was 10 foot tall? Well, we don't have square tubes, so we're just going to go back to a piece of pipe. Okay. My point is, it doesn't matter what diameter the pipe is, the head pressure, I shouldn't have said that, should I? The head of that will be the same at the bottom here, okay? So the column weight is probably another way of looking at it, will be the same at the bottom regardless of what size it is, okay? So if I spend the money, I put a nice gauge on the bottom of this, I get myself a ladder and a bucket full of water or a pitcher full of water, and I start filling these things up to certain levels, okay? Now notice, if I go back to that number I gave you before, a 1 foot column in this pipe, let's say it's a 3/4 inch pipe, is going to be just under half a psi. If I get my ladder out and I put some more water in there and I get it up to that magic number of 2.31 feet, roughly 28 inches, I'm going to be at 1 psi. That's why these two numbers we use for conversion. Okay, if we want to figure what psi is, based on I take 2.31 divided by, and the other way around, if I want to figure out what, if I have psi, I want to figure out what feet ahead it is just whatever psi I have times 2.31. That's why you'll see that in some of these equations, and you got to be familiar with that. Okay, and it's linear too. Notice 0.4332 or 4.33 at a 10-foot height. So just think of this analogy when you're looking at that left-hand column of a circulator performance curve. I won't get into this either, but those who remember who this actress is, and better yet, what movie this was taken out of, will bring you up to this next saying. Let's go up to the lab and see what's on the slab. Now this is just one of the little test benches in our lab. You know, we have the ability to test pumps as big as having a requirement of 20,000 gallons, right? So, I mean, we have two big buffer tanks. This is a little buffer tank, right? You can stand right up next to that. That's probably about maybe 5 or 6 foot tall. But imagine two 10,000 gallon buffer tanks that we use for some of our big pumps that we have to do sizing and flow verification on. So this is just a little test bench. You can see that they pulled the circulator out, and you can see this little catch basin and everything. So what I did is I drew this in a cartoon so I can describe what happens when we come up with a circulator performance curve. Okay, here's the buffer. Here's it's not just a flow meter, it's a very precise flow measuring device that gets down in the incremental gallons. Okay, then this is not a pressure gauge, but it's looking at the suction side or the inlet side. It's a pressure transducer, very accurate, very accurate for measuring PSI gauge. Okay. Same thing over here on the outlet side or the discharge side. We also monitor, this will come in later, we monitor everything there has to do with the motor. We monitor the voltage, the wattage, the RPM, the amps, all that stuff that's associated with this, the motor on this thing. We monitor that information. Okay, and out here we have a very precise valve capability. Think of it like a precise balancing valve or a calibrated type device that we can incrementally increase the pressure or release the pressure on something. So anyway, I set the groundwork for what we're about to talk about. So here's a particular circulator that was being tested, okay, up here, 0012F. Here's the y-axis, here's that x-axis again. Now, what the first thing we're going to do back here is we're going to take this valve and close it completely, okay? I'm going to close it, and then we're going to turn the circulator on. Mind you, all of the air is out of everything in this system. I've got a little air vent up here. Everything's gone. It's nothing but fluid inside there. I'm going to close this. I'm going to turn it on, okay? And then what I'm going to look at the pressure transducers, and I'm going to look on that the outlet side, and I'm going to see at no flow. Remember, that's how this reads. At 0 flow going this way, I have a resistance or the feet of head at 14. Okay, so that means it's going up to a top of the pipe. It's coming up right at the top of a 14-foot pipe, and it's holding there with just a little bit at the brim. Okay, that means it's pushed that water up that high. That's what I want you to think about. It's actually the differential pressure from whatever's on the inlet side to the pump, but it's as if it raised that water 14 foot. Okay, and then stopped right there. That based on that circulator at that RPM, at that horsepower, etc., that's what it has the capability of doing. And then, of course, electronically, we would make a mark right here. Then we go back to this thing, we shut the pump off, and now we open this valve all the way up, and we turn it back on. And now what are we looking for? 0 resistance. How much flow does this thing have? And of course, we'll make a mark there as well. Then we'll go back and we'll close that valve off a little bit, and we'll make another mark, and we'll close it again and again and some more and some more, and we'll eventually get the ability to actually draw in the blanks, and that's how we get a circulator performance curve. Okay, so it's based on very, very accurate information under laboratory test bench conditions. So I will say this, the circulator performance curve will be the most accurate representation of what that circulator can do or will do within a system. That's why, you know, when people call me and they say, Rick, can you just cross-reference a pump for me? Well, I kind of want to know what it needs to do, not because, you know, brand X, Y, and Z don't always match up. They don't always look the same. They don't always have the same angles or pitches, or, you know, whether it's a steep curve or a flat curve. You know, I might meet somewhere within that, but not be an appropriate pick. So I always want to know what the operating or the duty point is, and then I can better help somebody size the circulator. But you need to have your arms around this stuff. Okay. So anyway, so I realize it's just past breakfast. It's not lunchtime. It's what, 10:30 your time. So it's not lunchtime yet. But anybody take a look at that cut of meat and tell me what it is? Well, I won't wait for an answer, but I think most of you know what it is. Okay. I like it to call this the filet mignon of the circulator performance curve, and we liken it to the middle third. The middle third of this circulator performance curve is where we want to size circulators, right there in the fillet. Okay. The other thing that we want you to get out of this little session, you know, is don't size up here for as an an operating point. Okay, and don't size out here as an operating point. Okay, this will wear out the circulator and the motor and everything much quicker, and this isn't any good for it either. This is worse down here because it's having to do more work, but this is not good either. So try to keep your operating points to fall right in this middle third. Okay. The actual what we call our best efficiency point is right smack in the middle of that fillet. or kind of generally speaking, right in the middle of the circulator performance curve. Okay, so in this case, this would have the ability to do 27 gallons a minute at about 9 foot ahead, and that would be its BEP, or best efficiency point. Okay, and in this case, if that's where I was running, that would also be my operating point. Okay, and I could tell that if I knew what my system curve was. So that's what we're going to get into next. We talked about the circulator performance curve. Hopefully you feel good about that and have a good or better understanding of that. Now let's talk about what the system curve is, because you can see there's an interaction between the circulator performance curve and the system curve. And where they meet is where my operating point is going to be. So let's clarify what the system curve is all about. Probably the full name for it, let's see if I can remember how to call it, because everybody shortens it up. It is the resistance of the system that you put the circulator into. So in particular, right? So this is showing a boiler, a circulator, and 3 zones with corresponding returns from those 3 zones. And the pipe, the valves, the fittings, the links, the heat emitters, all that stuff is going to give a unique signature to this circulator. And that circulator going to know it as soon as it starts spinning. And within a few seconds, it comes up with a hydraulic resistance of that system. Okay, it comes up with what that is. It's not the same thing as calling it a CV, the flow coefficient, but I suppose you could, if you knew at a certain flow what the 1 psi drop would be, you could give this a flow coefficient. But we generally don't talk about it that way within this realm. So the system curve is a shortened way of saying the particular resistance of the system you put the circulator on. So shortened version is system curve. It's as unique as your toe print. Okay, I call that a toe print. Could be the heel print or a fingerprint, whatever you want to call it. But as unique as these are, is same as with the hydraulic signature of the particular pipes, valves, and fittings of the system that you put the circulator into. And I want to show you if I had all the zones open, I want to show you what happens on a multi-zone system when you actually start closing valves like zone valves. Okay, if a valve was to close, it changes, it kicks its way up. Notice how it moves from the right and up to the left. If another valve closed, you're going to get kind of the same thing here. And so I want you to understand, here's the circulator performance curve. How does the system curve interact with that? If it's running at maximum speed, it's going to go back and do the same thing I just showed you, up and to the left. Okay. Now, how can we predict where that's going to be? Yeah, there's a calculation for that. Just like there's an app for everything, there's usually some kind of a calculation to show you how to figure out what the system curve is. Now, in order to know, you must know one thing. You must know one thing, or do a pretty good estimate at one point, and then you'll get a fairly good, depending on how much good that information was, I should say, you would be able to calculate what the estimated pressure drop would be if you shoved more water through the system at a given point or less. And that's what this next slide kind of gives you an idea. This is one of our high efficiency circulators up into a light commercial application, the 1915E. And so let's put an operating point on there that we know. Pretty easy, 20 gallons a minute at 20 foot ahead. I want to know what additional resistance the system is going to impart on the circulator if I just raise the GPM up to 30 gallons a minute. I'm just going to raise it 50%. Okay. So one might think, well, if you raise the flow by 50%, the head's going to go up by 50%. So we're going to end up over here at 30 and 30. Does that make sense to you? Okay, that might be an intuitive guess, but in this case, it's not correct. Okay, we get into these things that are beyond what we really need to go into, pump affinity laws and things like that. But this whole square root thing that I'm showing you, things squared here, okay, kind of gives you a hint of where we're going with that. So this calculation looks like this. We're solving for the new head, which is H2. Well, in order to get that, we must know what H1 is, okay? And we need to know what Q1 is. This is where we got the 2020, okay? The new flow is 30, and the result of that we're going to square and then times it by the head. So this is how I write it out. This is how I like to do it. You can do it any way that makes sense to you. I have to establish what the first flow was and what the head was at that flow. Now here's the new flow, 30 gallons a minute. You take 30, which is the new gallons a minute, divided by the old gallons a minute, which is all I'm doing is this up here. That gives me 1.5 that I square. 1.5 times 1.5 is 2.5. The 2.5 now becomes my multiplier that I use against the old head. So I take the old head at 20 foot times 2.25. I can, if these numbers are good, this 2020 here, then you'll be dead nuts on at 45 foot ahead. So it wasn't intuitive. It goes way to hell up here. Okay. And you can use that same calculation backwards. Again, same calculation with half the flow would tell me where the new head would be. Look, and it's down here at around 5, less than 5 foot ahead. So 2, 4, 6, 8, 10. No, right at 5. 2, 4, right at 5. 5 foot ahead if I drop it back to 10 gallons a minute. So that's why you see these things that look like that. Now, some of our software that's in some of our commercial pumps, as well as our high efficiency ECM circulators, kind of use some of this information. Not so much the little ones, but like we get up into a big pump that has a variable frequency drive. That's kind of how it knows how to project and predict where the next pressure drop is going to be. All right. Again, if I don't hear anything, I'm just going to keep on going. Lastly, we talked about the control curve, and that's real simple. All that gets us up into variable frequency drives or ECMs, okay, the high efficiency pumps, when somebody might use this term. I like to call it an operating range, so it's not one more curve that somebody's going to get confused. But this would be in a constant pressure mode. We're showing you from here, it's just going to move back this direction, okay? Again, when I'm teaching it, I'm calling it an operating range, not a curve. What I mean, that's really not a curve. These are curves, okay? Because generally speaking, they're curved, and the system, it comes up here in a curve pattern. This is just a range of operation condition, okay? Now, let's not forget another very important thing here. We call this the point of no pressure change, okay? So there's 3 things that can change the pressure. And let me go back up just a little bit. What I'm talking about is this point right here. Notice where the expansion tank is meeting the system. That's showing here and here, but they left out in this drawing, or this picture doesn't show a gauge where a gauge should be. Okay, a gauge should be right here, as I've shown it here. We want that pressure gauge to be as close to the point of no pressure change as possible. So can I change the pressure there? Yes, add or remove water from the tank. That means if I let water in here, in here with this assembly here, that's going to change. If I add or remove air from the Schrader valve here or over here, this little blue thing here, that's going to change that pressure gauge, okay? Or if I light the boiler up, fire it up, and the system comes up in temperature, I'm going to change that gauge here, okay? Now, you would say, well, you just showed me 3 things that are going to change the pressure at the point of no pressure change. So why do they call it that? Well, you got to know what they were referring to, and what they're saying is, can the circulator change the pressure there by any of those three means? And of course, the answer is no. Okay. Here's a better idea of what I'm talking about. Notice here that I have the circulator pumping into the point of no pressure change. Well, we don't want to do that. Okay. Now, here's something that a lot of people can't get their head around. Okay. And I'm going to show you what I mean by that. Let's say I had that Bayos Fac pump, that big one. Remember the big ass one size fits all circulator like our 0013 or 2699 or something to that effect. And I'm looking at this, it's not running, and I'm about to switch it on. You would bet that I could take this needle and move it way to the right by putting that big pump on there and pumping into this point. And most people would agree. So I can't see you, but you're probably nodding your head that, yeah, I'm gonna move that needle. Now I'm going to say, no, you're not. And I've proven it with demonstration, and I'm going to prove it now just by an explanation. Okay. If that gauge were to move by that circulator coming on, wouldn't some of this water, remember the water is full, there's no air in the system whatsoever, then some of this water would have to move down this pipe, right? It'd have to be pushed down the pipe in order to change pressure on this. I think you can agree with that. Hopefully you can. Hope you can see it my way. Again, this has been proven over and over again. We do this on our, in fact, today's Wednesday. We have TACO After Dark this evening. I believe it's 4 o'clock Pacific time, 5 o'clock your time, 6, 7 o'clock Eastern. So if you folks want to do something tonight and get into some more hydronic stuff, that you can join us on that. So anyway, so understand what I'm getting at. You have to move that needle, okay? Well, in order to move the needle, you have to have water go down this pipe. If you were to have water go down the pipe, where would the water come from? It's already full. Would you get this perpetual more water entering the systems from some other location other than where it normally comes in? And the answer is no. So it doesn't matter how big this pump is, you're not going to move that gauge, okay, in this scenario that I'm showing you now. So that's why we're telling you, don't pump toward the expansion tank. All the mechanical energy that circulator adds is going to be taken away from the inlet side of the pump. Remember, this is a lean, mean, black and green pressure differential machine. It's going to create a pressure differential, but if it can't put it downstream of the circulator, it's going to pull it backwards, or it's going to pull it down on the inlet side of the pump, which is usually not desirable. Okay. And remember the same analogy I told you. Okay. If the water in the system is likened to links in a chain, then where would those extra links come from in order to go down that pipe and change the pressure on the gauge? Okay. So here's another analogy. I'm going to go pretty quick now, but I think you'll get the point. If the system's not doing anything, it's in a static condition. I got 12 psi on the air side of this tank, and I end up with 12 psi starting out as a static condition. I measure this 18.5 foot. I divide it by that number we showed you earlier, 2.31, because that turns it back into psi. I'm going to have an 8 psi drop up here at the top of this air handler. Everybody okay with that? If I started at 12 and I go all the way up here and measure the pressure, if I had the ability to measure it here, I would see that it dropped 8 psi. What's 8 from 12? Well, then you got your answer. You're going to be 4 psi, which is fine. I've got 4 psi up here at that air handler. There's nothing wrong with that. Okay, I've got a pressure differential. So when I turn things on, things might get a little crazy. Notice that when I turn it on, it starts out at 0 differential, but as soon as I turn it on, it pulls away that 4 psi. Now I take 4 off of that, I'm back to a big goose egg here. So, or I could be negative depending on how steep a pitch or, how is this a steep pitch or a flat pitch style circulator. I can actually go into the negative here. And if I have like an auto air vent up here with a cap loosened up, like some people tell you to, you can actually pull air into the system. So I'm just showing you, what happens. And I got to show you how to do it right as well, right? So here's a circulator that's pumping away from the point of no static pressure change here. That way, everything the circ can add will go out to the system, like I'll show you here. Okay. Let's say that now the circulator's here. I'm pumping away from the point of no pressure change. Remember, on the last slide, it was over here pumping into it. Now it's pumping away from it. Let's go ahead and see what happens when I add that 4 PSI. Okay, now it comes up here, it starts to get eaten away with friction loss and the weight of the fluid traveling up, okay? But it's still upwards of 6 PSI. I gain some PSI by coming down, but I get a little bit taken away on friction loss. Ultimately, by the time I get back to this point right here, I'm back at 12 PSI. So everything the circ's adding gets used up within the pipe, the valves, the fittings, and the friction loss of the system. Hopefully, this two-dimensional sketch will give you a better idea of why we want to pump away from the point of no pressure change. Anybody want to add anything or got any questions? All right, well, here we go, loop-de-loop. We'll get into the ECM essentials. Now, a lot of stuff that we talked about on the last two sessions is going to apply. So you're going to use that. I mean, I might just, refer back to it so that you have a better idea of why things work the way they do and how some of these. I'm going to turn my camera on just a little, for a second. We want you to understand that ECM has been a buzzword for, I don't know, 15 years now or so. Realistically, based on what's coming in Department of Energy requirements for the circulator that's less than 1 horsepower, is it's all about high efficiency. So I'm trying to teach myself to just call them high efficiency circulators in lieu of ECM. Call it whatever you want. I mean, we've been enamored with this ECM thing, but there's people using the term that don't even really know what it stands for. But ultimately, the point we want to make is that they're much higher efficient, and the efficiency out of these things are right out of the box phenomenally better. Okay, so 4-to-1, 5-to-1 comparisons. That's why you'll see, generally speaking, in some of the literature, they'll say that an ECM or a high efficiency circulator is, could save 80%, 85% electrical efficiency. So one thing to know for sure, generally speaking, right out of the box, you can take a standard efficiency pump and a high efficiency pump of the same style and same capacity, and the high efficiency pump will use 50% less wattage than the standard efficiency pump. That's running at full speed. That's why they say if you turn these things down, which they do either automatically or you can manually turn them down, you can actually get up to 85% electrical savings. So it's not so much the electrical savings. That's really not what we built our training platform on. Yes, they do save electricity, but they also save the fast cycling of the equipment. When the pump's oversized, it causes the equipment to bang on and off and on and off, and that system efficiency reduction we can gain back if we get nice long run time. So that's why a properly sized, a properly set up high efficiency circulator in the right mode of operation, etc., is going to be a winner for everybody involved. And that's why I put this session together called ECM Essentials. So you have to understand some of these fundamental things about a high efficiency circulator in order to take advantage of what they actually bring to the table. So, I'm just going to jump in and continue on. Unless somebody wants to interrupt me, feel free to do that. So what I'm going to get out of this session is just, hey, there's up to 5 modes of these circulators. Let's make sure you get those figured out and when to use them, okay? One of the things it tells you is how the system's piped, so I'm going to focus quite a bit on that, okay? The mystery mode tends to be the proportional pressure. I'll spend a little more time on that, when to use it and when not to use it, okay? We'll give you a little sizing example, and we'll dispel this myth of all these adaptable auto modes. And when they were first brought out to the market, they were overemphasized from the marketing standpoint that this is the only thing and the only mode you ever need to use. And that's what we've tried to do for the last 7 years, is dispel all that nonsense. So anyway, I'll try to do a good job of that. So understand one thing, that a high efficiency circulator or an ECM needs input. And what was the little robot that needed input? We need input. In this case, this circulator gets information off a couple of sensors. That temperature differential will be the input to tell that circulator speed up or to slow down. Okay. We get back over here. This is a delta P. This input to this one is going to be something that is going to be based on those hydraulic changes. Remember the hydraulic signature we were talking about? That's feedback to this particular type of circulator. That's going to be the input as well. Okay. And we'll give you enough information so you can make a good decision on when to use what mode of operation. This is not so much saying when do I use delta T and when do I use delta P. Primarily what we're using in this industry, except on rare occasions, is pressure differential. Okay. And that's what most of this training is going on. But understand, TECOS has temperature differential, and temperature differential as an input is still being used by some of the major boiler manufacturers that are using delta T to send a signal to a pump to tell it to speed up or slow down based on either it being able to keep up with a certain temperature differential, keep it tight enough, or to widen it up so you get those higher overall system efficiencies. So I realize I left my camera on, so that's cool. I'll turn it off and jump into this training. So I think a lot of you folks might wonder, well, how do these things, well, let me say it this way. If I made a statement that say none of these circulators read flow in gallons per minute, yet they have the ability to spit it out on the front of their cover, you'd say, well, how the hell do they do that? And that's kind of what I'm saying here. How do these things give us the ability to see gallons per minute and feet of head? Well, just in a couple slides, I think I could tell you that. Remember that same lab that we talked about? And remember that same mechanism for getting all the information to the what the motor's doing? Well, we can record all that stuff and we can data log that information. And based on running the pump through a bunch of different scenarios, we can log that information onto a particular circulator's curve. And so, for instance, if the circulator is seeing a duty point right here, it just simply looks down and reads the GPM and looks over here and says, hey, when I was on a test bench, this is what I saw, X amount of GPM at X amount of feet ahead, and it spits it out on the front of the unit. So guys, it's not that big a mystery. It's pretty simple. You say, well, how accurate is it? Engineering has told us it's within 5%. So 95% accurate. And that's as good as circuit balancing valves or those little, sight flow indicator balancing apparatus. We've got some. Caleffi's got some nice ones. Ours, you push in, there's your pull out. There's some good equipment out there, but the accuracy on those are about the same as the reading of these high efficiency circulators. Oh, anyway, so let's get into this. So the hydraulic pressure changes of the system is what a delta P circulator uses as the input to decide what's going on and whether it needs to make a change or not. Okay. Again, I'll use that term. Some people call it control curve, but it varies its speed but will stay on that operating range depending on the information and the input it receives. The three typical like baseline modes of operation are constant pressure, proportional pressure, and fixed speed. And these are the little icons that go along with that. You know, this would be constant pressure because you get a constant operating range that's straight across at a particular fixed amount of resistance. You see proportional because you see it's kind of pitched down here. That would be the fixed proportional pressure operating range. Okay, and then under fixed speed, then they're actually going to see a curve, and now all you're doing is you're turning or up or down the RPM within that particular mode. Okay, again, constant pressure, proportional pressure, or fixed speed. Now, what mode do I use? Okay, I told you there's up to 5, and I'm showing you the 5 of them here. Okay, constant pressure, fixed speed. I like to change that because if you use constant in a row, you might get it confused. So constant pressure, fixed speed, proportional pressure, 0 to 10, or these adaptable auto modes. And we'll get into all these and make sure you feel comfortable about them. Okay. Now, modes are either manual or automatic. Okay, so understand I'm going to give you, as these icons, I'm going to tell you when we're talking about a manual mode, I'll use that. And if we're talking about an automatic mode, we'll use that. Now, up in your upper right-hand corner of your screen, when I'm showing you these drawings, you will see these icons. So I want you to get your arms around this. And so when I start showing you something like this, you'll know what I'm talking about. I'm showing the icon here, and I'm telling you that it's a manual setting in this case. This is that. This is a good old 007, believe it or not. I think. Yeah, about just under 10 foot ahead and about over 23 gallons a minute. But this would be fixed speed. You know, it's got a maximum speed that it runs, a fixed speed that it runs at, and that's your circulator performance curve. Okay. Now, the reason I showed you that, I took you back, you know, to standard efficiency. What I want you to get your arms around is this. Look at what an ECM performance curve is, or a high efficiency circulator has the ability to do cool things like this. And Taco takes good advantage of this in a lot of ways that our competitors did not do. They're going to be copying us. It's just a matter of time because these are things that we can do and they can't. So they're going to kind of up the ante. We up the ante, and now they're jumping in with both feet. What's more important rather than maximum speed and minimum speed is everything in between. Okay, now they have the ability to turn themselves up and down in automatic modes, or in a manual mode, you have the ability to take it and just turn it down. Okay, and that's what we'll talk about here. So let's show you a system curve laid on top of all the circulator performance curves and the various RPM reductions. Okay, so if I'm running at maximum speed, this is where my operating point, in this case, my operating point. As I move it down, manually turn it down, I want you to understand what's happening here. Notice I've just chosen a lower RPM, and I can turn it down again and again, and I'm just choosing these subsequent lower RPMs. That would be a manual way of turning a high efficiency circulator down. Okay. Remember, they can do this automatically as well. This would be what would happen on a single zone application. When we get into multiple zone single system pump applications, remember what changes on the system curve. It's got to move up and to the left. Okay. So when is fixed speed an appropriate mode? People get this, they get kind of frustrated because fixed speed seems like something that you wouldn't want to pay the extra money for in the new high efficiency product when you could still buy a standard efficiency that's fixed speed. Well, I hope to change your mind there. They would say, well, I've got this fancy ECM, you know, that I paid a lot of money for. It seems a shame to run it in fixed speed. And again, no, it's not. And hopefully I'll give you enough reason why. Think back to what we said right out of the box, right? Right out of the box, these things are at least 50% less wattage to do kind of the same thing. And we're about to go into a new realm of even higher efficiencies that's going to help that as well. You're going to see that product start to meet North America here in the next few months, okay? So let's put little check marks by it. So zone pumping is an appropriate mode to operate when I have nothing downstream to give me any feedback. Remember what the feedback is to a delta P pump is pressure changes. If I don't have any zone valves out here or nothing's really going to change in a zone pumping application, I'm not going to get that feedback. That means that unit's never going to automatically do anything. So don't put it on an automatic mode. You may not get enough, or you may pump more than you need. So again, put zone pumping down there as an appropriate fixed speed. And you're going to get a copy of this same little sketch that reminds you, this little check mark reminds you that in this mode of operation is manual. It looks like this, and that would be an acceptable way of running those pumps if you're in zone pumping applications. Okay. Now here's one that I'm still talking about fixed speed. And I just heard something change in my headset, and I want to make sure I didn't lose you folks. So somebody come on and make sure you can still hear me.
We're still here.
Okay,
Rick.
good enough. Maybe somebody just muted or something, but just want to make sure I wasn't talking to nobody for an extended period of time anyway. We're looking at a heat exchanger and a domestic hot water circulator over here. Now, I want to point a couple things out. First thing is, if I'm still talking about fixed speed over here, do I put a check mark by that, knowing that I have feedback capable to give this circulator the ability to automatically speed up or slow down? And of course, I'm going to put a red X by that. If I'm still talking about fixed speed, I'm focusing on this pump, right? Notice all I want to do is get that coil hot, and I want to get it hot as quickly as I can. So I might adjust the speed of this to the GPM required to give me the recovery that I want on this particular tank. So you see why fixed speed is still an appropriate mode for indirect fired water heater application. Okay. There's nothing within this loop that's going to give this pump the feedback it would need in order to ramp itself up or down. So hopefully I made that point. Okay. Now let's talk about the boiler primary. We're talking about the boiler pump. Okay. Now many of the boiler manufacturers and your guys's in particular have some type of control signal out from the boiler to the circulator. And that's a good thing for the most part, okay? And if you have that, and I'll put a little caveat in there, if the circulator is appropriately sized, then you should absolutely use this. These are like, hand in glove. They just go well together, and you should use it. However, if you don't have that capability, I want to emphasize the fact that fixed speed is still the mode you should be using on this circulator if you don't have that capability. You have to have two things going for you. The equipment manufacturer has to have an intended output to run a circulator, and the circulator has to be appropriately sized and have the ability to receive that signal from the equipment manufacturer. So just those two things have to happen, okay? If not, then appropriately size the pump and put it in the fixed speed mode, okay? All we're telling people to do here is we're saying really sharpen your pencil when it comes to that universal hydronic formula calculation, the same one we did right at the beginning of the first session. And let's just do something. I'm going to pull my phone out, and I want you to pull your phone out as well and get to the calculator version. And we'll do something really simple here, okay? Let's take 150,000 BTU boiler. It could be 155 if that's the increment you're used to. So I'll use 155, 1, 2, 3 zeros. And I'm going to use the shortcut version of somebody sizing a pump on this application. Okay. I'm going to divide it by 20, and I'm going to divide it by, let's say, warm water at 490. What did you get in that? You got 15.8, didn't you? That's what I got anyway, and that sounds right to me. So people would say, okay, I'm going to put a pump in there that's 15 gallons a minute. Okay. And that's typically what a lot of the boiler manufacturers are going to do as well. And again, I'm telling you a couple things here. Scrutinize, follow what they tell you, but scrutinize what they tell you because of what I'm going to show you right here. This particular piece of equipment is a condensing piece of equipment. That manufacturer is going to show you that circulator can be much smaller based on a wider delta T. Let's do that same calculation again. 155,000. I'm putting that in my calculator. I'm going to divide it by a 30-degree delta T, and then I'm going to divide it by 490 again. That says I only need 10.5 gallons a minute. If this manufacturer allowed you to go out to, let's say, a 35 or maybe a 40, let's do that same calculation again. 155,000 divided by 40 divided by 490. I only need 8 gallons a minute for 155,000 BTU boiler. And that's only if I need to deliver 155,000 BTUs. Many times, my point of that is, many times the boiler is bigger than you actually need because, you guys as wholesalers didn't have what they only needed 138,000. You gave them a 155. That never happens. Of course, it happens all the time. So what I mean by sharpening your pencil when it comes to sizing of this particular circulator is size it based on the job at hand. That means at the altitude, at the required amount of BTU delivery for the job, etc. Okay, that's what leads these boilers, circulators, to be oversized, is just shooting from the hip, using 20-degree delta T's, etc., etc. So anyway, hopefully I beat that horse enough. So we're still in fixed speed. Notice over here, we're still in fixed speed. And we still have one pump that's not going to be in fixed speed. So we'll put a red X on that. But by all means, for the indirect and for the boiler for the boiler pump, okay, I'm going to use fixed speed. Is everybody okay with that? Okay. Again, you're going to get copies of this that'll help you remember what we're talking about. Okay. Now let's look at the first automatic mode, and we'll call that, this one, this flat one across here, is constant pressure. Let's put an operating point on there, and let's start closing valves. Watch the bouncing ball. It doesn't move in a flat line. It actually kind of hiccups. It goes up and then it comes back down. It goes up and it comes back down again because of what you told it to do. You told it to stay, in this case, at 10 foot of head differential, and that's what it's going to do. As the valves close, it's going to slow down. Notice it's grabbing these incremental slower RPMs, but it's keeping an RPM high enough to maintain the resistance on the system because it knows what it feels like based on the data logging that we put into the little chip that's within the circulator. Okay. Hopefully that makes sense to everyone. Now let's look at probably the primary application for constant pressure. I'll call this home run. Actually, it's not what I call it. It's Siegenthaler calls it that. Our industry calls it that. And what I mean by that is we have a boiler, we have some near boiler piping, and it's all in the same room with a header that's sized appropriately. And I've got 3 supplies and 3 corresponding returns coming back to the boiler room area. So all this piping here is generally short. Okay, so again, that's what we'll call a home run application. I touched on this earlier in the sessions that we did, and this would be one of these would set the precedent for what these would need to be. Which one of these zones is going to be the worst case, so this circulator would be appropriately sized. So in a home run application, we want constant pressure for this circulator, but we don't want it for that. That's why you'll see this over here, and you'll see the appropriate check mark by the circulator at hand. And why does it make sense to you if I know that if I want to be able to overcome the resistance under a design condition of the worst of these three zones, I'm going to have to maintain that because of the likelihood of that zone, the one that's the worst case, calling all by itself under a design load condition. So that's why we do it. Here's another look at a home run. This is more Siegenthaler kind of thing, you know, where he's got the flexible PEX or PEX aluminum PEX going up to a panel rad. Notice that the panel rads don't have TRVs on them. They don't have thermostatic radiator valves. All the zoning's done back here at the manifold. In this case, manifolds in the mechanical room. So now I have corresponding supplies and returns. I'm going to go through and calculate which one of those is the worst, and that's what I would set that circulator at in a constant pressure application. And the same thing applies here as well. Now let's look at proportional pressure. This is more the mystery mode. Same starting point here, but notice what the bouncing ball does as zones close in the system. Notice it's moving. It gets that little bump, and it's moving up and back down, up and back down. Notice it's going to a lower area potentially than if I had left it at constant pressure. So that's why we can confidently say this next statement, that proportional pressure mode will be the most energy efficient mode of operation, hands down. However, if you don't have enough flow in the system and you're not heating adequately, you have shot yourself in the foot. And so that's why we want you to understand to get the right mode so that you get the right flow under a design load condition. Hopefully that makes sense as well. So let's jump into this. Notice one thing too, generally speaking again, if I started here at 10 foot ahead at maximum speed, and the direction or the pitch or the angle that this thing came down got me down to the point of 5 feet ahead. 5 is 50% of 10, so this would be a 50% proportional pitch. Okay, and that's something that the manufacturer of the circulator, like Taco or Grundfos or anybody else, would preset within their algorithm of their pump, okay, or the brain within the pump. Now, when is proportional pressure appropriate? Okay, now notice I've changed the name of this layout pattern. Notice this is, you know, generally you would understand what an extended header would be, because that little header that was in the mechanical room on that last example I gave you is not the same here. Notice, let's say that these are the escutcheons and I'm leaving the mechanical room. I got a boiler, I got a supply pipe, a circulator, and I'm leaving. And I'm going out and I got a bunch of pipe out in the building, okay? I'm picking up all these different supplies and returns and everything, and it's all coming back, and I got a single return coming back. So I could stand in the mechanical room, I can look at this thing. If I know I only have one pump and I've got one supply and one return, yet you know it's a multi-zone system, you can make a pretty good assumption at midnight on New Year's Eve that this system is piped something that's similar to this, okay? Now, with that in mind, you have to recognize the fact that this circulator right here is going to be affected by all of this supply and return piping, right? So let's give you a scenario. We had a design condition during the night, and now it's becoming daylight and it's clear skies. It's cold out, but yet the sun's coming up, and it's got solar gain on the east side of the building, which it's facing, okay? And now every other one of these zones starts to close, okay? Well, if I have the circulator in the appropriate mode, the circulator is going to feel those zones closing, and what's it going to do? It's going to slow down. Now, is that slowing down of the pump going to create more or less flow in the header? Of course, it's going to create less flow in the header. When we create less flow in the header, is that going to be more or less resistance that the pump is going to see? Well, of course, it's going to be less. And guess what? That's why this pitch up here works good for these types of piping where you have an extended header, because as the zones close, there's a reduction of flow. A reduction of flow is a reduction in pressure drop, and the pump knows that and can feel that and gradually works its way down to a lower RPM. So hopefully that helped explain that. There's one form. This is a 2-pipe direct return. It could be 2-pipe reverse return. Either way, it's still all the same. Again, look at it. This is showing ModCon, pipe primary, secondary. Here's the escutcheons of the return coming back. Here's the escutcheons of supply going out. Regardless of what's happening out here, it could be thermostatic radiator valves, it could be zone valves. It's more about how it's piped than what kind of control device is on there. That's been a little misleading because we're catering to the Northeast, where they tend to use more thermostatic radiator valves. And of course, that kind of lends to the fact that it's an extended header. They've shortened some descriptions up, which unfortunately can cause some misinterpretation of what mode to use. So keep that in mind as well. Us, as well as others, are making what I feel, in my opinion, is a slight mistake there. We're catering to one area of the country and not everywhere. So anyway, I better shut up before I get in any more trouble. Here's another version of the same thing. And this is kind of more of what you'd see in Europe. And that's kind of why this proportional pressure mode is out there, residentially speaking anyway. So you got all this pipe that's out here. You got the mains, you got the branches, you got the twigs, you got the TRVs, you got the panel rads, and this circulator is going to fill every bit of that. So as these panel rads modulate open and close within the system, notice this just keeps going. Then it's going to feel that and it's going to ramp up and ramp back. Notice another thing that I'll say here. Generally, a lot of these systems, because they're thermostatic radiator valves, they don't have end switches that come back and shut things off, right? So that's another consideration there for why this circulator might want to run continuously while there is a possibility of a call for heat. We'll say that the only thing that brings these two circulators on would be the outdoor sensor of this particular manufacturer of condensing equipment. Could be any brand, but some of them push that more than others. So. Okay, everybody good so far? Should I pause for a second there? We're not going to have time for another break. We only have another 40 minutes and I've got plenty to cover there. So you can excuse yourself if you have to. I'm gonna keep talking. Okay. Everybody okay?
Good, Rick. Keep rocking.
Okay. Okay. All right. So what happens when we choose the wrong mode of operation? Okay. So notice I've given some numbers here, and this is purely hypothetical: 9 GPM, 14 GPM, 12 GPM. I'm staying with the 3 zone because I want the picture to be big enough. You could call this could be multiple zones out here, but let's say that we need 35 gallons a minute, and at 35 gallons a minute during a design load condition, I'm going to be at 13 foot ahead. You can see how I got that information by adding these numbers up. That's all given here and up here. Okay, so this pump, this system circulator, needs to give me 35 gallons a minute, 13 foot ahead. Now let's map that out. 35 gallons a minute, that's 30, and there's 40, so somewhere in between there, right? 35, and there's my head, and there's my operating point under a design load condition with everything calling. So make sure you get that. Okay, that's the worst case. And if we're doing our load calculations correctly, we're doing our design correctly, appropriately, and we're not going to throw a bunch of fudge at it, right? The only time we're going to need this operating point, ASHRAE tells us about 2.5% of the season. So at 97.5% of the time, this pump is oversized. That's why we want to use it to its greatest ability for turning itself down and slowing down and giving us better overall system efficiency. All right. So there was the operating point under design load condition. Now let's show the operating point if that zone that had the greatest pressure drop called all by itself, and we'll show you where that new curve would be. Okay, so what is it? About 12? That's 10, 11. No, that's 12, between 14 gallons a minute, I think it was, somewhere 14. And that's where we got that head number from, right? So that's where we want the operating point to be if that zone calls all by itself, which it could. You have to realize that. We have to design for the worst case. Okay. Now, watch what happens if I should have put it in constant pressure, but I didn't. I left it in a fixed proportional mode or an automatic mode that was proportional pressure. Okay. Now remember what the bouncing ball does? It works its way down, works its way down, works its way down until you reach this point here. Now notice you no longer have the GPM that you needed for this zone. You can see the difference here. You no longer have the GPM and you no longer have the head. So you really wanted to be up here like this. This drops you back down here and here. That's why we're saying if you had have chose the right mode of operation, look how much closer you would be. This would actually move right up here. And then you get this movement across here from here to here and back. Hopefully that explains it in pictures, and you'll have a better idea of why and when to use the right mode of operation. So some other ECM realities, right? There's no such thing as a magic button, right? Again, I think I dispelled that already, just saying, hey, there's no one mode that works for everything out there, and hopefully this little session has helped you with that. We also don't call them smart pumps because there's really nothing inherently smart about the little algorithm that's put inside the circulator's chip, right? Again, it can't balance for you. It can't size appropriately. You know, there's a whole lot of stuff we've already talked about that it can't do in what some people are attributing as smart. And that's all we're saying. You know, we want you to be smart. We want you to understand what to do and how to manipulate these high efficiency ECMs and get them set up right for both, well, everybody in the industry, the owner of the building, the owner of the installation company, you know, the contractor, and so for somebody who's designing systems. I spend a lot of time doing engineer lunch and learns in our bigger pumps, and one of the things I'm trying to constantly get the engineers to do is put the actual mode of operation that they want within the circulator notes. Out on the right hand side we have a circulator or pump schedule, and out on the far right you have the notes that can be they tell you, well, this is what we want to happen, this is you know, some general statements. They have the flow and the head and an operating point, all that stuff in there, but they've got a place for the notes out on the right hand side. And what we want to happen there, more importantly than anything, is that they're telling the person doing the commissioning or the startup what mode of operation they had designed the system for. Because if they don't put that in there, the people starting the system up are not going to know, and they're just going to leave it in whatever mode that the circulator came out of the box in. And guess what, folks? Most of us manufacturers, many of us included, are going to put it in the supposed smart mode, and or better said, the mode that gives us that adaptable auto feature. Okay, so anyway, I hammered that home a lot, I suppose. Adaptable type auto modes. Oh, okay, we call ours active adapt. Okay, You folks know about Grundfos's Auto Adapt. Velo just came out and called theirs within the last year or so, called it the Dynamic Adapt. Armstrong just calls it Auto. Okay. B&G or Xylem call it, they just branded theirs the E-Adapt. We might rebrand ours from Active Adapt because that's something we've got from our Italian brethren and folks. We might call it something different someday, but that'll remain to be seen. But for now, it's Active Adapt. Okay. What my point is, they're all basically the same thing. They all kind of do the same thing, and that's what I want to emphasize the most is you can blow it with all 5 of these manufacturers. And there's other manufacturers out there that have some things too, but these are what we would consider the primary people selling product in North America at this time. All right. So first thing to remember when we're okay. So what I want you to picture is, should I keep the adaptive auto mode in operation when I pull it out of the box? Okay, so that's the question. Do I want to leave it in the mode it comes in out of the box? Well, I've given you all kinds of criteria to make that decision, but let's emphasize it even more now when we say, look, make sure, this is where the biggest mistake has been made with our product and others, is they forget this simple thing that when the manufacturer shows you this little wedge, this shaded in area, what they're saying is that's the only place the pump's going to operate. So if all of a sudden you have a requirement for to be here under your design load condition, the last thing you want to do is leave it in the adaptable auto mode. Does that hopefully that makes sense to you? Again, that's the one thing hard about doing webinars, and I'm so happy to be back doing in-person training. In fact, I'm going to come out and see you folks in February, as long as everything stays the same and we're still back out there in front of people. I've been on the road for probably at least 8 or 9 months now, and traveling almost every week. And I'm just saying it's great. But my point is, I can't see you guys nodding or not. So hopefully this makes sense to you. Okay, that's why I told you to interrupt me if we need to. Now this proportional slope, I'm gonna just give you a little heads up, but this is a little advanced information, but it doesn't really matter, but it's kind of nice to know. Now here's one icon, okay, that shows that wedge of operating condition. Here's another way of showing it, okay, and here's another way of showing it. Regardless, I want you to recognize something. I'm gonna put the word fixed on these two, and I'm gonna put variable on this one. What I want you to look at is, notice how, for instance, over here, this comes to a point, this comes back at a particular pitch. This comes back at a particular pitch, but ends right at the same spot. Notice these two have kind of fat back ends on them, okay? So it reminds me of a song. You guys can type in if you know which one I'm talking about. But notice this is fatter back here than it is over here. Nothing wrong with that. Okay, it's just showing you that this pitch is fixed. They're not changing the pitch. Whenever you see something that comes at a point like this, the manufacturer has a variable pitch. For instance, this is 50% on some of our product, and when it comes up here, it goes to 70% pitch. So just that's a little extra nugget of information you're probably not going to get from anybody else. So another thing to remember, we're back. I started to read something. Anyway, first things first, when to use auto mode. We're still talking about that. The other thing to make sure of is what we just kind of finished on, was understanding that there's different layouts. Okay, there's some different layout patterns, like we talked about. There's extended headers. There's home run type layouts. There's hybrids. Hell, we even got monoflow applications out there. And so you need to know whether or not the adaptable auto mode would be suited for that type of piping arrangement, and let that be one of the first things that helps you make a decision whether you use that mode or not. All right. Another thing, this actually plays to a particular type of control mode for like zoning and stuff. Or I was telling you, I kind of showed you that European type piping that showed a wall hung boiler. It showed a low loss header, 2 separate circulators, and a bunch of panel rads with an extended header type design. Remember that I said that some of those don't have in switches, right? If I've just got a pump that's turning on based on an outdoor temperature and it's going to spin, whoever put that note up there, I'm not hearing anything other than myself. So anyway, yeah, go ahead and I think it said Chris was making noise in the background, but I can't hear it. So anyway, I tried to catch that note. Like I said, I've got it. It's pretty tiny on my screen, so hopefully I read that correctly. Anyway,
I think they're just giving him a hard time, Rick. I don't meaning mute him on the chat.
Okay. All right. I'm going to let somebody else worry about that. Anyway, thank you. As long as I can't hear it, it's not bothering me, right? And that's typical, right? So as long as these things are working in a way that's going to give you long run times, I believe, you know, Tecmar's a good example of some of their control strategy that they use. They use the, you know, zone synchronization and zone staggering, and they try to keep the zone that has the greatest demand running on almost a continuous basis. Now, the other example that I was referring to earlier is that if the only thing that turns the pump off is a warm weather shutdown condition, then that you got to know that pump's running continuously. So with these long or extended run times, the algorithm of the circulator has the ability to make some good decisions based on seeing flows increase and decrease and head increasing and decreasing. So it can gather enough information based on being a delta P circulator that it can make decisions to not only slide up and down a fixed proportional run, you know, operating range, but it can now decide whether it's going to step up and down the runs of the ladder. So within those shaded areas, those wedges of operating condition, you actually have little adjustments in the pitch of those. And I like to call them steps of a ladder or rungs on a ladder. So when you're in these adaptable auto modes, you're making 2 different moves. You're moving up and down the range of the particular fixed pitch, and you have the ability of changing that pitch. So that's what's happening. But my point is, a lot of these algorithms are set up to not kick in and do any changes until the pump's been running a sizable amount of time. So what I'm getting at is, if you're set up in a situation where your zones are going to call for heat, they're going to open, the pump's coming on, and you're going to satisfy that zone in a matter of, like, you know, 5 or 10 minutes, and you're going to shut back off again, you've not given that algorithm enough time to make a decision whether to step up and down on the rungs of the ladder, right? So just understand that concept. So again, I'm building the case that says, look, you know, don't just use the adaptable auto mode because it came that way out of the box. We want you to put some good thought into appropriately setting these systems up. Okay. Now, next thing to acknowledge is that these are delta P pumps. So again, if they don't have any feedback in the form of hydraulic changes downstream of the circulator, there's no way these things can make a good decision whether to speed up. In fact, I know what our pump will do, and I'm pretty sure, being delta P pumps, this is what all circulators would do, regardless of the brand, in particular modes of operation, is they just going to come up somewhere in the middle of that wedge. You know, if it's an adaptable auto mode, then somewhere right smack in the middle of that wedge of operating condition is generally where the pump's going to start out. If it never gets any feedback on zone valves opening and closing, etc., it's going to stay right there. Okay, it's never going to move. It's going to operate, and it's not going to give you what you think you're getting, even though, and I'm going to do quotations and you can't see me, you're using the magic button, or the one button that fits all application. Anyway, I'm seeing notes pop up, and I'm okay with it. It's a slight distraction, but I can see some humor in there, and that's a good thing. We don't have enough of nowadays. So keep it coming. Anyway, so if you understand that pressure differential is what the input is for these automatic modes of operation, then you got to make sure you're going to get some. Okay, so you can't use it if it's a zone circulator. Okay, you know how many circulators that come out of the box in these adaptable auto modes and just set on a zone pump application, and in the back of their mind, they're thinking that they're getting all this feature and benefit, and they're really not, right? Because they don't have the feedback that's needed. Okay, so zone pumps, they're out. Don't use it for that. Don't use it for as a boiler circulator. I already told you why, right? Boiler circulator. The only two things that want to run a boiler circulator, and a boiler circulator would be either the 0 to 10 volt or pulse width modulation, or some kind of signal from the boiler manufacturer to the boiler primary circ. Then it can speed up and slow down with instruction from somebody else. And you got to think of it that it's almost like us being the circulator manufacturer hands the keys over as far as control is concerned to the boiler manufacturer. So unless that's happening, you want to stay on fixed speed, and you don't want to put it on an adaptable auto mode. Same thing applies to heat exchangers. Normally, any kind of heat exchanger, depending on which side of the heat exchanger you're on, there's never really a reason to vary the speed of the pump. Now, we were varying the speed of some variable speed injection circulators into the heat exchanger for doing snow and ice melting. The one thing you got to be careful of there, you better make sure you have glycol on both sides of that heat exchanger, because you'll freeze the side A of that heat exchanger up really fast if you're not careful. So be careful of that. And domestic hot water indirects, they're just another form of heat exchanger. We typically want to satisfy those as fast as possible. We want to get as much flow through that coil as quickly as possible. And if you think about the circuitry, the piping scheme of those, there's nothing in there to give the circulator any feedback to make a decision. So again, take the ECM and put it in a fixed speed or an appropriate mode that makes sense for the job at hand. Okay, same thing applies for fan coils or unit heaters or anything like that. That's why I have these signs here. Don't use these adaptable auto modes on any of these applications. They typically are not a correct match. And you say, well, I've done this and it's worked fine for me. Yeah, it might have worked. All that means is you never had any errors. The boiler never locked out. But you have to ask yourself the question, how much better could it have been if I had put it in the right mode and I got the circulator to turn down to the mode that was more appropriate? So anyway, hopefully that helps. And this is just to kind of wrap things up, just to say, look, we've still got you covered up to about 300 gallons a minute in ECM technology. So there's a bunch of stuff out. I want you folks, you don't know about some of the newer things we have, the 007, the 0015 E3, and the 0018 E available in stainless steel now, and in two different connection configurations. We've got the 1-inch BSP half union connection that you can do some cool stuff with, and the universal flange configuration in stainless steel. I didn't know if you knew that. And we've actually updated the VR series. This is fairly new from last year, but because of supply chain issues, we're having the same problems a lot of other people is. So, but just understand that That's a fairly new item for us as well. And this is where we get up into about 300 gallons a minute. This would be something that we would go after the Grundfos Magna 3 with, so up in the bigger pumps. Okay. So I think that's all I had for you. I got done quite about 20 minutes early, but we can use that time for other things, or we can give you that time back, like we like to say in the world of webinars, right? We'll give you that time back, and you can do whatever else you want to do to make some more money. And if you're done listening to me yak. So anyway, go ahead and those who want to talk, turn your mic back on, and let's wrap this thing up one way or another, or ask some more questions.
Thanks, Rick. Nice job.
Well, you're welcome, and glad to be part of it.
Keep in mind, everyone, too, that, we covered, calcs, pipe sizing, pressure drops, CVs. We also talked, curves, selections on pumps, where pumps belong. We talked on ECM essentials. There's also other topics that we could incorporate. We kind of tried to keep it in the 3-hour time frame. There's domestic hot water recirc classes. We could do a thing on buffer tank sizing, how to get more runtime on your boilers, indirect domestic hot water sizing, ModCom boiler piping, primary, secondary type stuff. Obviously, we're going to be covering a lot of it in the heat summit. I just wanted to say that, if we want to go further, Rick, is there also one on multi-zone and controlling as far as when and how to use switching relays, ZVCs, those types of conversations?
We could resurrect some of that, absolutely. And then again, as that product gets some updates down the road and stuff, we'll be highly focused on that, because there'll be some cool changes and stuff. But yeah, we could do something on that, or we might get our old buddy Dave Sweet to jump in and help us with that sort of thing. It's just something that we haven't done on the typical TACO Tuesdays or TACO After Dark sessions, but we could absolutely resurrect something, or hang out for a while and see what else comes our way. So,
okay.
But we sure could do something. Yeah.
Okay, I'll work with Northwest on that and see if there's interest that we, even go one step further.
Yep. Yeah. Okay. Anybody else?
Yeah, guys, I just wanted to mention, bone up on how Sure Start works. Because, when I'm out talking to contractors, and I get questions all the time on,
Didn't we
why
talk about muting this guy?
That's probably the most important or easiest way to get guys to really even consider going to ECM versus a standard, fixed speed wet rotor circuit.
That's a good point. I mean, we got time now. I've got a session I could just go through real quick and talk about what that does. I could just do it off the cuff as well. But and sometimes pictures are handier. But let me do something real quick here. Just go into something that would have that in it already. And let's see, where do I cover that? Cover that in. Let's go down to this. You can still see my screen, I'm assuming, right? And I kind of cover that right at the end here, and let me open this back.
When we've done counter days, we've taken pumps apart and we put a pigtail on it, plug it in, and let people see how that oscillates too. It's always a good idea.
Okay. Most of these pumps that we have will have one type of we'll have a couple or both. We'll have both of these or one of these features I'm going to talk about right now. And the first one is one that kind of gives us a leg up as well, and another reason to consider these when it comes to North American water systems and stuff. And there was some initial talk about dirty fluid quality and things like that. So it has a solid ceramic shaft. This looks like a hole, but it's not. It's just a little point on the end there. The fluid actually enters up underneath this impeller, and I'm going to show you a picture with this impeller taken off of there, and you'll see where this thing we call black iron oxide barrier. So when I say bio, I'm not talking about some kind of disease or something. So the only thing that you have to be assured of is that there's only one series of these pumps that it doesn't come in, and it doesn't come in it because of the application they're primarily for, and that's domestic hot water. So the stainless steel versions of the little 44 watt platforms don't have the BIO barrier in it. But okay. So here's pulling the impeller off. This, unfortunately, when they took this picture, I wish this was white, but it kind of looks like the same color. Hopefully it's rendering good on your end. But this is actually like a media, like a brass media that's very tightly pressed together filter. As similar, it kind of reminds me of you folks that will go back a while when we used to sell oil fired equipment. We had an oil nozzle that the nozzle itself was made of these little tiny brass pellets that were smashed together, and that was atomizing. But it could also be looked at as a filter, and it's kind of like that is what this material kind of reminds me of. Okay, here's the back side of it, and here's the actual motor. Here's the electronically commutated motor. There's the ECM, right? And notice that this is where, back underneath this thing is where the fluid would come through and would give you the two things that the fluid does for a wet rotor circulator. It gives us cooling, and it gives us lubrication on these shafts. So the shafts are lubricated and the motor itself is cooled with the fluid. So we want to make sure the fluid is nice and clean, at least on the initial startup or the commissioning of the system. So again, protects and does what it's supposed to do. Not to say that I've never seen one of these gooped up. Now, again, the filter media does a really good job, but it only goes a job down to 40 microns. And 40 microns is actually pretty small. If you look at it, it's about the size of the pollen that's floating around, causing our eyes to water and sneeze, and for our bodies to start attacking and giving us fits for. So understand, when we're talking microns, we're talking really, really small stuff, but there's some of that bio or black iron oxide that would be smaller than 40, and so that's again, that's problematic with anybody's stuff. Even, you know, this is self-preservation type design, but we can only go so far to do that. And it's done a really good job for the most part. And again, we're reasonably sure people are going to copy us on this feature as well. Here's what the Sure Start feature that I think was brought up that we want to focus on, locked rotor condition. So if anything, let's say bio, or it could be a big slug of solder or a pebble or a piece of wood chip or something was to ever get up into the circulator where the actual impeller is at, the motor can feel that. And the motor feeling that, it has the ability to change its direction. It'll oscillate. And what we mean by that is it'll change direction. It'll go from forward to reverse, to forward to reverse. And it'll do it in these little split-second bursts, and it'll go back and check and see if it was able to dislodge anything that was stuck in there. Now, depending on which series of pump, if it's a little 44 watt smaller units, it tries 100 times in about 15-minute period to break itself free. If it doesn't, it just locks out. It'll give you a red lockout light, but it won't sit there and burn itself up. The 20 times is for the 170 watt platform, which is that bigger 26E and the 34E plus and the E platform. So the bigger platform with that little square thing looking control on it is 20 times, and the littler pumps will do it 100 times, and it's approximately 15 minutes. At least that's what the literature actually says. So Again, you get that many tries and then it just locks out. The good thing about it, when the service tech gets there, he sees this red light. It doesn't mean the pump's bad. He's just going to disconnect power to the pump. He's going to take the pump apart. He's going to get what I would say, try starting with the power head, pull that thing apart, find out what is it full of black iron oxide, or is it just got a wood chip in it or a rock or something like that. You clean that up. You clean the power head up. You make sure the O-ring's in the right place. You put that thing back together. You repurge the air out of the circulator or the system, depending on how you have it piped and isolated. And then you start that baby back up. That resets the counter, and it normally you take off and you're running again. You're not throwing pumps away at that point. So it's been good for us, and it's the main reason. Like, let's say, for instance, Vimco doesn't have a pallet and Northwest Pipe doesn't have a pallet of these bad circulators sitting in a corner somewhere for the bone pile. And again, we've had this series pump with these features out for approximately 8.5 years now. So I came on board, I've been here over 7.5 years. I came on board right after we released it. So I'm guessing 8.5 years, this feature and benefit within this pump. And to the best of my knowledge, in over 7.5 years, I don't know of a bone pile sitting anywhere. We've actually have looked at some of these that have come back, but it's nothing like the standard efficiency product of our brand as well as other brands that you typically will see bone piled in the back of the warehouse somewhere. So anything else, folks?
You know, Rick, this would probably be a good thing to bring up during the Heat Summit for sure. You know, just kind of hit over this or touch on it.
Oh, I'd be glad to do that.
Yeah.
I do really use this as like a jumping off point, because I do get a lot of questions on why should I even go ECM. I've designed everything up until this point in my life with, you know, around fixed speed wet rotor circulators. Yeah. And, you know, you can talk to them about efficiency and you can talk to them about varying speed and all of this, but really that's been the one thing when I tell them that, you know, circulators aren't inherently bad. They just, things change in the system, and they don't know to, you know, they'll tear themselves apart. Yep. And when you say that, you know, this circulator actually won't, it'll recognize these situations and lock itself out and allow you to come, you know, resolve the issue and then put it back into service. That right there gets contractors' attention probably more than anything, when they realize that, you know, they don't have to have a whole bunch of 007, you know, cartridges on the shelf. They, you know, start using ECMs and they go out and they resolve the issue and put those circulators back into service. So
yeah, no, I appreciate that, Chris. That's good stuff. Yeah. Good stuff. So anything else,
awesome,
folks?
Thank you, Rick. Appreciate you.
Glad to help. Glad to be part of it, and look forward to seeing you in a few months. All right.
Thanks everybody for your time and your participation. It's appreciated. Have a great day.
I'm gonna, I'll get this recording when they send it to me, and I'll get it to you guys. And thanks again for your time. For the folks back in Rhode Island, thanks for your support. Okay, take care of yourselves.
You guys too. Rick, we'll see you in a few months.
Yeah, looking forward to it.
Thanks. Bye, guys.